Hello. Good morning, everyone. Welcome to this morning's session on net zero. So this subject, of course, is highly topical and hugely important, and perhaps represents the greatest challenge water companies face over the medium term. So most of you, I'm sure, are all too aware, but the English and Welsh water companies have made public commitments to be net zero by 2030. And Scottish Water have made similar commitments to challenging carbon targets. The good news, of course, as will be illustrated this morning, I'm sure, are that there are some fantastic innovations coming through which will help us deliver on these commitments. So I'll very shortly hand over to the important people who are going to be telling you all about these innovations, but just to remind you that there will be the opportunity to ask questions after the presentation. The presentations will be 20 minutes and we've got 5 minutes for questions, and I'll keep an eye out for any questions that come through on Hopin. So without further ado, it's my pleasure to introduce our first speaker, Ellen van Verthausen, apologies if that's not quite right, of RHDHV. Thanks, Ellen.
Thank you, Peter. Yeah, you set yourself a major challenge for 2030, net zero, and I'm happy to share the results we gained in the Netherlands. The nitrous oxide emission seems to be some uncertain things around it, but past and present papers show that we can get started. How we can get started, that's what the presentation is all about. And before I continue on that, just the first small introduction to our company. we will celebrate our anniversary in about 2 weeks of time, and then we exist 140 years as a consultant and engineering company. Within the water domain, we have a broad package of consultancy service from water security resilience towards wastewater treatment, and that's the domain I'm working in. And it's a nice anecdote in wastewater treatment, a small bit of history. In 1913, 2 British scientists invented the activated sludge, which we still rely on. And we have been working with that invention as a company as well in many projects. We learn a lot from that. And then, I think by the end of the 19th, Mark van Loosdrecht, professor at the Technical University of Delft, invented the granular sludge. And together with us, based on our experience, and of course with the cooperation of our clients back in the Netherlands, we developed that granular sludge towards a robust technology. And this is just an example in the way we work. Our consultancy will always be our basis for our products, which were just an example are given here. So back to the consultancy. Since I started at RHDHV at 2007, and almost directly after that I got involved in the process emissions from wastewater treatment. The first research was done in 2008 on 3 covered plants, so we did some off-gas measurements, and then it was followed up by a really long-term measurement campaign at 1 treatment plant in the area of Rotterdam, where we measured continuously nitrous oxide and methane from the off-gas, again a covered plant. And this research learned us that there is a huge variation in emission throughout the year, and it showed a rather high emission. So the question was, is this treatment plant really representative for the Netherlands, or is it just an exception in its high emission? And in the Netherlands we don't have that many treatment plants as you, around 300. But it's still really costly to start measuring nitrous oxide at all of them. So that's why we developed a simple risk model. I will come to that a little bit later. And finally, on methane, we set up a practical guide about how to estimate the emission of methane throughout the wastewater and sludge treatment. And we also worked out some mitigation strategies. So the rest of the presentation I will focus on nitrous oxide, and by the end of the presentation I will come shortly back to methane as well. What I said, there's something about nitrous oxide, I think it's too complex, we don't understand everything yet. But I just picked up 2 review papers, one back from 2009 of Kamsgreur, and one from the UCWA report that was published recently. And what you can see is that the parameters that were pointed out as important for that influences nitrous oxide are still the same after more than 10 years. So I think that shows, that those papers show that there are some clear directions towards risk assessment, which can help you to select sites, but also already give direction towards some mitigation strategies on nitrogen load, aeration control, and the level of denitrification. Our first step in mitigation is, of course, getting your emission estimated. And as I said, just starting to measure everywhere is very costly and labor intensive. So you can select sites based on the simple risk model we developed. If you have nitrite and ammonia data of your effluent, with this table you can estimate if your plant is on a low risk, medium, average risk, or a high risk. And we just give an estimate of the expected emission factor. You can just use it to select, and you always need to measure afterwards, but it gives you a first insight where to start measuring and mitigate. We verified this model in the Netherlands, 2 measurement campaigns. The first one, Soerendonk, had an average risk based on the effluent data, and the emission factor showed so. And the same for Nieuwegein, that was based on the effluent data a high-risk wastewater treatment plant, and the emission factor was high as well. So the measurements proved the use of the simple risk model. So then we can go through to the lessons we learned. Oh no, first one more. So this is the simple risk model is a way to estimate your emission, but then the next question is, do we need one or more emission factors? This is a nice overview published recently and collected by Vasilaki in 2019. It shows the different process types from the left to the right. And you see there a huge variation between process types, and you see quite a variation within one process type. So the question really is, should we focus on one or more emission factors, or should we just getting started, learn a lot, and then see if we need emission factors in the end? So the first lesson we learned, I think, if you look back and look forward from literature, I think on the left there's a paper from Burgess, Cranfield University. It was published in 2002. And in the upper graph, you see the relation between the ammonia load versus, on the left axis, the nitrous oxide, and on the right y-axis, the specific nitrous oxide production. You see a clear linear relationship between the two. And in the lower graph, it's a bit pity that I can't walk, but anyway. In the lower graph, you see the presence of nitrite, which are the open squares. So here you will show the presence of nitrite when you have a shock load of ammonium. And when you look at the right side, that's the research we are performing right now in the Netherlands at the treatment plant of Soest. In the upper graph, what you see is that in the first period of the research, the plant received an additional 25%. Still working? Okay. The plant received an additional 25% ammonium load because of a side stream work that didn't work at another treatment plant. So it received 25% of its normal ammonium load. And you see that the appearance of nitrite. So this is a bit the same as the picture in the left corner there. The effect on nitrous oxide we couldn't clearly see because you also see the seasonal effect as well.
Can everybody hear Ellen? Back of the room? Can you use this mic?
Yes, I think so. Yep. Is this better?
It's not on, is it? I think they need to turn it off. Sorry.
Couldn't see. Is it working? Yes, it is better. Okay, so what you see in 20 years' time, still the same relationships can be seen between ammonium load and nitrous oxide emission and the appearance of nitrite. So the first lesson is avoid high ammonium load. The second lesson is a good aeration strategy will pay off. From the same paper of Burgess in 2002, she turned, oh now I can walk, that's better. As he turned off the oxygen, and immediately you see a rise in nitrite and nitrous oxide. And when the aeration is turned on again, nitrite and nitrous oxide both disappeared. And on the right side, you see on the upper part, in the first part, this is plant in the Netherlands. The aeration strategy was based on a minimum oxygen level of 0.5 and a maximum of 2.5. Those were the settings at the first part. And they switched the setting towards 0.5 to 1 as a minimum, and they decreased the upper one from 2.5 till 2. And then you see a quite drastic decrease in nitrous oxide emission. So here you see the impact of DO set points. And the lower graph is the work we did on one of our narrator plants in the Netherlands. And what I just want to point out in this one is during the winter times we see a quite high variation. on top of the regular. And then we applied a different process control to stabilize the DO a little bit more. And then you see that this variation disappeared. So the basis is still there, but the variation is gone. And one other interesting thing to see here is that the level of emission in the winter time is quite equal to the emission in the warmer months. So there might not be a direct effect of temperature, but an indirect effect. As in the winter, the activity of the microorganisms are lower, while the solubility of oxygen is better. So that makes it probably a bit harder to control your DO, which results in a higher DO variation. I think this is a graph probably quite some people already saw, especially the one on the left. This is the third lesson, ensure a good denitrification. The left graph is the work we did in 2010. There's a strong seasonal effect and a year average of 2.6%. And the measurements were repeated in 2020. What you see, you still see the same seasonal variation a little bit, but you see a drastic decrease in emission. That almost decreased from 2.6 to 0.5. And I think the major difference between the two periods was the way the plant was aerated. So the wastewater, the sludge, came from a plug flow reactor into this carousel, hits the first surface aerator, which was on all the time, and depending on the ammonium concentration, these two surface aerators were switched on or off. So you get a very heterogeneous oxygen profile throughout your tank. And somewhere in between this period, they replaced the surface aerator by bottom aeration. And as an effect, aerobic zones become really aerobic, and anoxic zones really become anoxic. And that might explain the big difference between the emission factors. One really last nice slide, I think, on nitrous oxide at least, is this one. I think that's a paper published recently, and the work is done in an SBR. So we might keep an eye on that, but I think it might teach us some nice lessons. On this graph, you see the dissolved nitrous oxide running throughout the aerobic period, and as soon as it hits here the anoxic zone, you still see an increase of nitrous oxide. So this implies that nitrous oxide is even also produced during the anoxic zone. And it remains stable for a little while, and then you see a quite sharp drop in the dissolved nitrous oxide. And if you then look back to the cause of it, it happens exactly at the same point nitrite disappeared. And then, so the lesson is, give enough space to denitrification. First to denitrify your nitrite, and then you enable also to denitrify your nitrous oxide. So give enough space to denitrification and will avoid emitting nitrous oxide. And they saw some relationship with the pH and the conductivity, but those are both measurements that are not that costly. So that's something to look further on as well. So the take-home message for today, let's get started. I think the previous slides show that past and present papers give some good directions. You can start doing a risk assessment to help you with site selection. We can start up experiments to mitigate nitrous oxide emission. On avoiding high ammonium loads, a good aeration strategy, and giving enough space for denitrification. And of course, we have to continue with scientific work for an improved understanding. And I think we were talking about yesterday a long time about phosphate and the use of BioP in relation to N2O. Biological peer removal in itself doesn't convert any nitrogen in the end. What are risks with biological peer removal in N2O is if you don't have a long retention time in your anaerobic tank, some easily biodegradable COD will flow through your anoxic tank, and there it will convert the nitrite quite easily and produces quite some nitrous oxide. So if you just have a long enough retention time in your aerobic tank, you won't have any risk on N2O afterwards. And during your aerobic stage of the biological phosphate removal, you just have to take care of a good oxygen profile. And if you do that, you also almost diminish the risk of nitrous oxide. So BioP in itself will not produce N2O. It's just the way it's operated and designed that might influence it. Then first, we didn't stand still in the Netherlands since the last research. We erected a community of practice in 2019, and we almost complete. 17 out of the 20 water teams are involved. At around 11 wastewater treatment works, the N2O is measured, and we already have valuable data collected. 7 wastewater treatment works already have a data set of 1 year. What we do in this COP is we really exchange knowledge and experience, and the water authorities are doing the work here. They share experiences around the measuring protocols, data analysis, and mitigation strategies. And we are cooperating here with the Technical University of Delft, who's really looking at the microbiological level into the emissions. And then, just to conclude, don't forget methane. I have been talking about nitrous oxide up till now, but I think this is an important message as well. These graphs show the avoided or emitted carbon dioxide in time. The green dots are the avoided carbon dioxide by the production of electricity via CHP, and the blue dots represent the methane that was emitted after the sludge digestion from the storage tanks. And what you see at really certain points that the avoided CO2 was nullified completely by the emission of methane. On year average, it was 60% of the avoided CO2 was nullified by methane emission. So thank you for attending, and looking forward to see you in person as well after this conference, as I will move to the UK for the 1st of November. So hope to start working with you on this topic.
Brilliant. Thanks, Helen. Yeah, a really clear articulation, I think, of the challenges that we face with process emissions, but also some of the advancements that we can make to hopefully get closer to net zero. So I've got no questions yet on Hopin, so I shall hand to the floor. Has anybody got a question for Ellen? Thanks, Amber.
Hi, Ellen. I find that really fascinating. Thank you. Do you have any kind of quantification of how much opportunity there is to reduce nitrous oxide emissions from what we currently operate at, and whether there's always going to be like a minimum level that we can achieve, and there's going to be a baseline that we can't avoid?
Yeah, there will always be a baseline, because nitrous oxide is just part of the nitrogen conversion in a treatment plant. But we can minimize it quite, I think whatever, I think I showed some pictures. I think even up to 90% is possible, but it really depends on how highly loaded is your plant at the moment, what kind of aeration strategy do you have. So yeah, I think you can make some major steps, but you always keep at a certain level, but then the contribution to the carbon footprint is also very small. In the Netherlands, not more than 5%.
Got time for one or maybe two more questions?
Wendy, MMB. Yeah, great presentation, thank you. Practically, how are you doing the measurements on the 11 treatment sites that you're testing? You know, are you doing dissolved N2O, or is it you're
it's all
actually
dissolved.
catching the gas?
It's all dissolved, yeah.
Okay, thank you.
Thanks. Time for one more, if there is another question. There you go, Amanda.
Hi, Amanda Lake from Jacobs. Thanks, Ellen. Really, really fascinating topic and great presentation. I just wondered, looking forward, what do you think? There's obviously the great need to just start monitoring and collect the data set that we know we can. But what do you see? I think there's a lot of potential for innovation, and you've talked about some of those. What do you see as some of the greatest potential, I guess, innovations in this field over the next few years, or as we approach net zero?
Innovations in this field?
Yeah, in the mitigation, or the way we're monitoring, or the topic of process emissions.
I think you can make use of existing. We didn't talk about the side stream treatment. That's, I think, not that positive for nitrous oxide. But real technological innovations to avoid moving away from biological treatment. Go towards physical chemical treatment. My colleague will talk about that later today. But that faces some other challenges. But yeah, getting away from biological is probably the best way to get rid of it. But that's some decades ahead.
Thanks very much.
Can we show our applause for Ellen once more? Thank you. Thanks, Ellen. So next up is a face that needs little introduction. I'm sure most of you know Pete. And Pete's going to be talking about how perhaps an older, established technology might help us. So over to you, Pete.
Thank you very much, Peter. Sorry, is this one on? Is this microphone working? Yes, it is now. I can hear it. Okay. Right, yeah, thank you for that. So, skipped a slide already. Right, okay. So, yeah, so here we are. So I'd say, first of all, good morning, conference, and good morning for my co-author, Gong Yang, as well, who's not able to be here today. So, yeah, we've heard lots of shiny new technologies, and I'm here talking about trickling filters. So no great change there. So going to get there in a... Why doesn't it like that slide? Excuse me. Right, okay, so some context. So, yeah, obviously I could tell you that trickling filters are an essential part of a low-carbon strategy going forward, and they're sustainable, etc. But be that as it may, we've got an awful lot of them. There's 7,000 or so plus trickling filter plants in the UK. They're still the mainstay of wastewater treatment, particularly in the smaller rural areas. And they're not going anywhere soon. Even if we found the ideal process to replace them all tomorrow, we're not going to replace them in an AMP period or 2 or even 3 AMP periods. So the sooner we get to understand how to control them and predict what their performance will do, the better. In particular, because as we know, they're getting challenged with more and more stringent consents, especially on the small sites, many of which they weren't designed for. So what we're going to be talking about today, as the title alludes to, this is part 2 of a presentation, the first one made at last year's conference, which looked at seasonal variability. This is looking at day-to-day variability, and very much from a consent point of view, our regulatory framework is dominated by performance at the 95th percentile or lookup tables, and so understanding variability, is absolutely key to understanding the risks of compliance. So this is very keen to jump 2 slides at a time. Okay, yeah, so just a quick recap in terms of where we're coming from. The model which we now refer to as the Tunbridge model was developed, and that gave us a good explanation of the seasonal variation that we see on pretty well all sites. Once you've got some good online monitoring and you see good performance data, you start to see the trend that we show below. And basically the model explained that seasonal variation due to 2 factors, an empirical model, but the 2 key factors behind it. One was the fact that the filters are producing less solids in the summer than they are in the winter, so the load to the humus tank is lower. But by far the biggest factor was the fact that we have a temperature-driven physical effect on the humus tanks, affecting the reducing viscosity, reduces the settling velocity of fine particles, and trickling filters produce lots of fine particles. And we see, so this is a typical trend of modelled versus monitored effluent quality over 5 years, and we can see the model is actually fitting that pretty well for a trickling filter site. It's predicting the magnitude of the peaks and troughs as well as the timing of them. So this study, or the short-term variability study, I'll skip through to the next one, was extended, now covers 43 sites, 5 or 6 years of data on each site, 15-minute data compiled into sort of daily averages, gives us something like nearly 100,000 data days, of which we did the modelling. So in terms of the variability, there are 3 examples here. So on the left, the first one we see, the model predictions in red, showing a reasonably smooth humus tank effluent output, but actually the monitored trend we can see here in blue is showing that we got a lot of very high variability throughout the year. These are 1-year periods for these sites. The one in the middle is showing reasonably smooth effluent variability, and believe me, for a trickling filter that is reasonably smooth, certainly compared to the last one, and that's been predicted by the model. And on the far right-hand side, we can see we've got, again, quite a noisy trend in blue being picked up by the model. So the important thing is the one on the left, there's lots of stuff going on here which isn't picked up in the model. In other words, it's beyond just a simple hydraulic loading on the clarifiers, the organic loading on the filters and temperatures. You know, this is the variability that we're trying to get to the bottom of. So there are a couple of challenges when we try and, what we need to do is try and compare the variability between sites. So there's a couple of challenges. The first one being that standard deviation is sort of typically used as a good measure of variability, but it's in engineering units. So because these sites are operating at very different baseline performance, if you like, due to their different loading, we can't directly compare the standard deviations. You need to do something about that. And the second thing is that this day-to-day variability is around the cyclical seasonal variability that we see. So we need to try and improve on that as well if we can. So how we got around that? Reasonably simply, to get round to allow us to compare between sites, we took the standard deviation and just divided it by the average to give us what a term we call the relative deviation, or RDEV, which is what I'll be discussing or talking or referring to through the talk. So that then gives us, instead of standard deviation in engineering units, it gives us relative deviation as a percentage of the mean. And to get around the cyclical seasonal variation, we then calculated this RDEV statistic on 30-day rolling averages. So effectively, we sort of broke down the cyclical seasonal curve into straight line sections. And that gave us a reasonably good measure to compare. It's not brilliant, but it's a good enough measure of variability to allow us to compare the different sites. And that gives us the ability to then to look at what's driving that variability, why some sites have low variability, why some sites have very high variability. And we sort of picked factors which we thought might impact on it, and they are the filter flushing velocity, or SK value, the siphon, whether the sites were siphon operated or not, the site size in terms of population, daily flow variability, and irrigation velocity, otherwise known as wetting rate. And so typically the sort of numbers we're getting for this RDEV 30 statistic were between 0.2 and 0.8. That means that the variability was adding another 20 to 80% on top of the seasonal average. And the seasonal average itself might be adding 60 or 70% onto the annual average. So it gives us an insight into that and allows us to compare different sites. So going through those quickly, the question was, this is now looking at variability on the y-axis against flushing intensity on the right axis in terms of Spoolcraft number. And the question was, you know, if we flush the filter well at the surface, does that help keep the filter clean, prevent solids accumulation, and give us better variability? The answer is pretty well no. Nearly all of the filters are running at very low SK values because they've got quite fast rotating reaction drive distributors, but even on the sites where they're slower, where we've got motorized distributors or paddle wheel distributors, we're not seeing a tendency to either increase or decrease the variability. And probably more importantly, all these sites here at quite low flushing intensity show the whole range of variability. So there's obviously more to it than just that. For siphon operation, a similar story really. We've plotted the siphon dose sites scored 2, the non-siphon dose sites scored 1, with variability along the bottom, and they both show pretty similar distributions. This is obviously a smaller data set. There were about 19 or 20 sites out of the 43 which had filter rotation monitoring on them, allowing us to look at the Spoolcraft number and a similar number with siphon, which is siphon operated as well. So we next looked at site size, which is a reasonable stab. We all know that bigger sites have lower variability and smaller sites have the risk of having much more variable flows. They might have 6 dry weather flow or all dry weather or all flow consents. And we're starting to see a little bit of shape here, but not much. We can certainly see the sites, and we get over 10,000 up to 100,000, tend to be having lower variability. But even below 1,000, we've still got the full range of variability. So some of these very small sites can still show very low variability, as well as some of them obviously being very, very noisy. So again, there's more to it than that again. But when we start digging into that a bit more, if you now start looking at the flow variation against the effluent quality variation, we start to get a little bit of an insight into what's going on. Small sites can be expected in some cases to have very, very reactive networks. You can get very high flow one day and it can drop right back to average flow or even dry weather flow the next day. And so when we plotted that, again, we can see here that the sites, yes, with very high flow variability are getting high effluent quality, effluent solids variability to an extent the other, but it's very, very noisy. There's lots more going on, and the R-squared value is not particularly good. When we then looked at wetting rate or irrigation velocity, what this does by including recirculation, a lot of these sites with high flow variability, if they have recirculation, that variability will be buffered out, because on a low flow day, the recirc will kick in, and on a high flow day, it will drop out. And this really gave us, that's really brought a lot of these outliers in, gave us a very strong relationship. And what we can see very clearly now is that, the sites operated at low wetting rate, around sort of 1 metre per day, one and a bit metres per day, are very much showing higher effluent solids variability. And that reduces very progressively down to an optimum wetting rate between 2.5 to 3 metres per day. And interestingly, as we increase wetting rate further, the variability starts to go up again. But this is now, you can see we've got an R-squared statistic of 0.77, and certainly in my experience of modelling trickling filters, that's getting fairly good, because there's lots going on here. There are 43 operational sites. It's all the data, warts and all, so there'll be other things going on. So that is actually, that's quite a tight curve. Just talk through that one. So, but interestingly, and in parallel, if we completely ignore models, if we completely ignore spurious statistics that might have made up, like relative deviation, this is just looking at the effluent quality data. This is a 95th percentile over the mean from the turbidity or suspended solids trends over 5 years, and the 5th percentile over the mean. And there's two key things here. The first one is we can obviously see exactly the same relationship. So the sites with a very high 95th percentile to mean ratio, the ones that are very erratic, are the ones operated at very low irrigation velocity or wetting rates. We're coming down to the same optimum, and also we're kicking up again. But interestingly, from a sort of mass balance perspective, the 5th percentile to mean absolutely mirrors that. So these sites here, which we think are accumulating solids at low flow and then shedding them, giving these high solids and high 95th percentile to means, when those filters aren't shedding solids, they're accumulating them. And actually, when they're accumulating them, they're filtering them, and that's reducing the load onto the settlement tanks. And so these very noisy sites are actually producing better effluent at times at the 5th percentile level than the ones which we would say were optimized. So that really gives us a little bit of confidence in potentially what the mechanisms are, and also what the findings are with the development of relative deviation. The fit is obviously a lot poorer on these, because we're now looking at the whole year, we're looking at the whole seasonal. We've got the cyclical seasonal variation within this as well, so the fit is poorer. But it's interesting, a parallel approach is giving us a similar output. So what we almost certain those mechanisms are, these are empirical models, so these are all proposed mechanisms, but almost certainly what's going to be is that we're seeing at low wetting rates, we're getting solids accumulation within the filter itself. It's acting as a physical filter. So solids going onto the filter or biofilm sloughed off isn't getting flushed through the filter, it's getting intercepted, it's getting caught in the interstices of the media, and we're getting unstable solids accumulations which just get pushed out next time the flow goes up a bit or the flow changes. A typically designed filter, if you're thinking of sort of 45-30 consents or even 30-20 consents, if you don't have recirculation and you've got normal reasonable strength sewage, the wetting rate actually is very low. They're operating at one and a bit meters per day. And that's now right in the sort of territory where potentially we've got this, we can get solids accumulations at these lower flows. And the higher flow, be that diurnal flow, the diurnal peak or even the slightly highly daily peak or over a few days will push those solids out. Mechanisms at high flow rates, we'll leave that open to discussion. My opinion is it's probably due to the fact that we've got quite high scouring in certain parts of the filter. It's not allowing the biofilm to mature, so you've got unstable, immature biofilms in lots of the filter, in parts of the filter, which is allowing it to come off. But there's very few data points on that higher wetting rate. It's certainly not as strong a relationship as we see with the one at the lower wetting rates. So applying that, this is a very typical output from the Tunbridge model. So this is showing the model trend in red, the monitored trend in blue over 5 years, showing, giving you a fairly good account of summer peaks and winter lows, both in timing, in terms of timing and magnitude. This is a reasonably quiet, a reasonably non-noisy effluent curve. And what the RDEV statistic allows us to do is now put bounds on that average that we are modelling, the seasonal average, in terms of an upper and lower limit, which is equivalent to sort of 95th percentiles and 5th percentiles as well, for that matter. Not that we're interested in 5th percentiles, we only get caned if we exceed the 95th percentile. But what that does now gives us effectively a range, and this particular site is operating quite nicely within it. We can see the blue monitored data is pretty well within the green and red bands all the way through, which suggests that the model is actually accounting for nearly all, not just of the seasonal variation, but also of the day-to-day variation that we see by incorporating wetting rate. So the applications of this, there's an obvious one for design. With the progression of models from the base model through to the Tunbridge model, and now with variability, that allows us to look to design humus tanks for annual average and seasonal average, but also now to get a good access to what the 95th percentile is by applying the variability model. And that's really key, not just for the humus tank effluent if it's discharged directly, but the humus tank effluent as it applies load to a downstream tertiary treatment plant. Because what we see is the fingerprint of variability for the humus tank effluent exactly replicated on the fingerprint of the outlet of the downstream tertiary treatment effluent suspended solids as well. So with the increased sort of focus on TSR for either for phosphorus removal or solids removal, understanding the humus tank output is particularly important. For optimization, it allows us to look at a site and actually predict what the improvement in variability and therefore consent compliance is going to be if you optimize the recirculation or introduce recirculation in the first place. And from an investigation point of view, which is what I'll look at on the next slide, it gives us a bit of an insight. It allows us to break down a high 95th percentile value to see what its components are. And I'll skip through that fairly quickly. Hopefully you'll see these slides and it'll make a bit more sense when you can read it. But what we've got here is two sites, both with an effluent 95th percentile of about 25, 26, but two quite different sites. So the black box at the bottom is what the base model is predicting, and that's really just down to asset capacity. That's down to the filter, the organic loading onto the filter, the function of load and filter volume, and the hydraulic loading onto the humus tank is a function of obviously the flow and the humus tank capacity. That gives us effectively the annual average, and that's a model that's been well established over many years. On top of that, the grey bar is a seasonal, the additional seasonal, the impact effectively in the winter in this case, so the additional solids coming out due to the effluent being colder. This is the Tunbridge model output. And again, same, this is modeled for winter, so this is adding on to the mean. If it was summer, it would be subtracting from the mean. And then what we've been talking about today is this herringbone pattern bar, which takes account of the variability. And we can see on the site on the left now that the models are accounting very nicely for all of the 95th percentile performance that we observe, whereas on the right, very importantly, these are adding up, but it's still short. And it's very important that there's another box, which is stuff that the model doesn't account for. And that's actually quite valuable. One, because it allows us to use a model as a screen to pick up where sites aren't performing as they should do, or as we would expect. But also, in this particular case, so all these factors, the base model, the Tunbridge model, the variability model, still show that we should be doing better than we are. And in this particular case, this site, it was down to real extreme diurnal flow variability was causing the problem. But it could be down to mechanical problems, sticky distributors, that sort of thing, or seasonal stuffing, actual, genuine spring shedding as we see. So effectively we can start using this model as a bit of a screen. Yeah, very neat there, Pete. So just to finish up now on discussions and on some concluding points. Variability is vulnerability as far as consent compliance goes. So understanding variability really is key to understanding what our risks are. The variability model really gives us a good insight into what's driving that variability on site. Wetting rate is probably the key factor. Doing that almost certainly the key factor, and by controlling the wetting rate we can reduce that variability. And the mechanism almost certainly solids accumulation and flushing, which will occur at these low flows. And so this model, with the Tunbridge model, which gives us a seasonal variability, this one gives us a short-term variability. On the 43 sites we looked at, that gives us, that covers explains very well nearly all the variability that we see, both long-term and short-term. But nearly all, but not quite. There are always going to be exceptions, and I'll leave you with this chart. This is, again, the upper and lower percentile, if you like, predictions. And on this particular site, we can see the blue curve is actually exceeding the upper variability limit regularly. And that regularly is actually each spring. So this is one of the very few sites that we found that actually had genuine spring shedding occurring. Because out of the 43 sites, nearly all of them, we could account for the seasonal variation by the model factors, not by the classical, if you like, spring sloughing. But this is one site which does appear to exhibit it. So again, that's really use of the model as a screen, as an investigative tool. So I'll leave it there for questions. Saying thanks very much to Don for his support through this Water for making this very extensive library of data available, and there's a huge amount of information in monitored data if we can spend some time looking for it. Thank you.
Thanks very much, Pete. So I think that showed very clearly the power of a really detailed analysis and the building of a model. So any questions? Amber.
Hi, thanks, Pete. Really interesting. I'd be really interested to know, have you differentiated between works which have ferric dosing and those which don't? And if you, because we do see a difference in performance between those sites, and also if you did, are you able to differentiate or pick out the transition from a non-ferric site to a ferric site when we bring that chemical dosing on to predict?
Okay, so I missed the middle part of that.
Did you differentiate between sites which have ferric dosing and those that don't?
Yes, we did. Obviously, short presentation today. The upshot is actually it doesn't impact on the variability. Now, the variability as a percentage of the mean, effectively, covers quite a wide range. So some of these sites have quite high variability, but the actual mean might be very low, so it doesn't really matter that much. But when we actually, if we highlighted all those dots, as in some of them ferric dose sites, some of them not, you'll see they're fairly equally distributed above and below the line and along it. So it doesn't appear to make that much difference now. If that answers your question. Was there another part, Amber? Sorry.
It was just if you did see the transition, are you able to predict what we would need to design to for sites where we intend to bring on ferric dosing? But if you don't see much difference, then...
Yeah, I mean, longer term, once everything's evened out, so obviously if you change something on the filter, it will take quite a period of time for it to fully acclimatise. The ferric dosing will lower the overall average. So if you like, all of those bars should come down slightly. And certainly, by reducing the loading onto the trickling filter, if we're dosing at the front, that will bring the overall annual average down. It will bring everything. It should bring everything down. But the variability, as we can see, even some sites with very low averages still have very high 95 percentiles, and that's down to the variability. But so the ferric dosing should bring everything down. By bringing the base average down, it should drag the other numbers down. And again, I have seen that, in practice, you do improve humus tank effluent solids if you reduce the load onto the filter.
Narinda.
So Pete, a quick one around the model itself. Does it differentiate between circular tanks and pyramidal tanks?
That's a very good question. No, it doesn't. And the original models, so all this really was, there was original base model, and then that was a platform. We put the tonnage model on top of that and the seasonality on top of that. The original model was based on scraped circular humus tanks. So, yeah, I'm sure you appreciate the difficulty of putting a huge data set of particular pyramidal tanks or particular horizontal flow tanks. So in answer to your question, no, it doesn't. We can... or you can, if you think there's a particular performance factor in that in terms of the surface loading. The problem is that we're talking real-term operational data, and yes, you would say generally a pyramidal tank is less efficient than a half-straight circular humus tank, but there's an amount of overlap. A well-operated pyramidal tank will actually operate a lot better than a poorly operated circular tank. And so even shallow horizontal tanks can and do produce very good effluent if they have the necessary maintenance. So there is an awful lot of overlap. But to answer your question, no, the model doesn't. The model is based, the original model is based on circular half-bridge scrape tanks, and you can put a factor in if you want to at that very early stage to adjust the performance. And I do, on the model spreadsheets I use, I do have a box where I can factor in a shape factor effectively. Yeah. But it is just
Sorry,
that.
Can I also ask you to comment on, so trickling filters, N2O production,
yep,
and the state of media as you see it, because you do get to see a lot of sites.
Yep.
Do you think there's perhaps N2O production on sites that perhaps aren't as well maintained, or where the actual condition?
Very good question. Absolutely no idea. Measuring, I have discussed this and sort of talked to people about it. Measuring N2O production on filters is going to be very difficult, because you need to measure, or let's say if you're measuring the gas phase N2O production, it's very difficult because you never know quite whether there's airflow going up the filter, down the filter, or no airflow at all, which happens for quite long periods of time. So I think, judging by the talk earlier this morning, if we start looking at measurements of dissolved nitrous oxide, then that would probably be the way forward, but I haven't seen any numbers on that, so I really can't comment. Yes, there is an oxic and potentially anaerobic activity going on some, particularly at lower wetting rates, and obviously there's nitrification going on, so there will be nitrous oxide emissions, but what they are, I don't know yet. Area for research, more work required.
Generating loads of interest, so loads of questions. So at the risk of overrunning slightly, there was a question from the hopping platform along the lines of what type of filters have you modelled, Pete, in terms of the media type, and have you noticed any variations?
Right, that's interesting. These are predominantly stow media filters, but actually within that data set there are two plastic media filters. And once you factor in there's a general performance factor for plastic media filters that they operate at about 2.5 to 3 times the efficiency of a normal stow media filter, that sort of order. Once you factor that in on the wetting rate, they actually fit exactly, they do much the same as the others. But to answer that, it is predominantly stow media, and I wouldn't certainly stand up and say this is going to exactly happen on plastic media filters, because they're often operating quite differently. So this is mainly traditional stow media filters, I think I would say. Yeah.
Brilliant. Thanks, Pete.
Okay.
Sorry, Martin, I think we'd better move on, so I'm sure you can catch up with Pete.
I'm sure you can catch up with me later, yeah. But yeah.
Thanks again. So our third presentation is from NVP Energy, Alan Rogers, and I think and Connell Holohan, and they're going to be talking about the really exciting subject of anaerobic treatment.
Morning. Is that working? It is. Right, okay. I thought I was going to be the rock star again for a minute. Morning everybody. Spoken to a handful of the people here online over the last 6 months, various meetings to talk about anaerobic. I'm Alan Rogers, and I'm with Connell Houlihan, soon to be Dr. Houlihan. And we're here to talk about MVP Energy, which is the company we work for, and our wastewater treatment solution, which is known as Ambirobic. And the subject is, how have we, as Ambirobic, achieved low temperature, low carbon, low cost treatment of municipal wastewater? Where's the button? Oh, there it is. You can, just briefly, this is quite nerve-wracking. I've done this loads in my career, but I've not actually been out of my house for about 2 years. And I'm just introducing it. Connell's doing most of the work. So, why are we here? We're obviously here to debate and discuss new ways of doing things which benefit the wastewater sector. Now, Ambirobic, it's just the biggest step in net zero carbon. And the reason I'm here, I'm a civil engineer, I worked for a big civil engineering contractor for the last 20 years, is I was very fortunate. I went to Antarctica 4 years ago. I led a bid, we won the bid, we went to the site, and we've now constructed a big new wharf down in Antarctica. But it was absolutely compelling, just seeing how global warming has reduced the glaciers that sort of front up at the base that we went to. You can imagine it was an absolutely stunning visit. But what it did for me at the ripe old age of somewhere in my 50s, it really connected me with the net zero. So 4 years on, I was given the opportunity to join MVP Energy. And it's these numbers, and it's the compelling debate about energy saving, getting rid of sludge in processing sewage, and reducing greenhouse gases, absolutely massively. And on top of that, you get significant capex savings and absolutely massive OPEX savings. So I'll leave you to the person who knows all about it. He'll take you through how we've got there and how it works. And at the end, any questions? Thank you.
Thanks, Alan. So thanks very much for having us. I know there's more than one expert in anaerobic technology in the room, so delighted for you to grill me with questions after this. But first of all, let's introduce it. So Ambirobic, created by MVP Energy, and behind that, 20 years of research. So we treat wastewater. We don't treat sludge, is the first thing to say to you. And we are the first in the world to do it at low temperature. So you think anaerobic, you think sludge, you think biogas. So somewhat correct, but we do not treat sludge with this technology. We treat wastewater. So we're anaerobic wastewater treatment, post-screen treating crude sewage. So it's a little different to what you're used to, but we are an upflow system that treats the liquid phase using a granular biomass. So these are our babies, our bugs, and they work by converting BOD into biogas. So you might know it in your brewery wastewater, your dairy wastewater, or your paper mills, treating high-strength wastewaters, but treating it at 30, 37 degrees, removing high BOD, converting it to lots of biogas. And that's correct. That's what's been happening, and that's the typical anaerobic wastewater treatment plant. However, some of you who know it a little bit more will know in tropical countries that they can treat sewage wastewater like this. So you go to Brazil, and they utilize anaerobic wastewater to treat their sewage. And they do this because they can, because it's more concentrated wastewater and it's warmer temperatures. And they do this in around 800 wastewater treatment plants down in Brazil, and this is one that's treating 1.2 million PE. And why do they use this? Why do they not just do what we do up here and go into your ASPs? And it simply comes back to these figures. Because they're able to utilize anaerobic treatment, they don't produce sludge. The BOD goes into biogas for them. They don't have to aerate, so they don't use energy in aeration. And therefore, with those two put together, they obviously save significant CO2, which is coming down the line. So we're here to tell you now that you can do it in Europe. You know, to date, the question has been, what about temperate climates? Why can't we do it? What's limiting us? You know, so it was down to the wastewater. So you're way more dilute. Obviously, we have a lot of infiltration, but even before that, we're way more dilute wastewater. So our COD is less than 1,000 megs. And you all know that if you put your hand in sewage, it's pretty cold. So it's 4 to 15 degrees. And simply put, for bacteria, that wasn't good enough up to now. So the bacteria weren't able to operate. They were normally operating at 30 to 37. In the Netherlands, who were leading this for the last 30 years, they would have tried it several times and it failed. Simply the upflow systems would not work. So you were getting washout of the bugs because of the temperatures. There was a lot of question over whether or not the conversion would happen. Would the BUD go to the biogas? So there was a microbiological ability. So NVP Energy, Ambirobic, we've been an overnight success. We've managed to prove this over the last 20 years. So it came from NUI Galway on the west coast of Ireland. Back in the early 2000s, they came at it from a different point of view. They came at it, right, we have bugs here. We know that they're there in the system, they're there in Antarctica, and they're working away producing methane. How can we make these guys work for us at those low temperatures? And they did it. They showed, first of all, it can be done at low temperatures between 4 and 15. So that's possible. The conversion rates are there. You just need to give them the right environment. So then they went and they built a reactor around them. They built a technology around the bugs. So, as I said, overnight success, 8 PhDs, 35 man-years, and then they came along and they patented a reactor design, which is Ambirobic. So it's come along, and NVP Energy was set up. They licensed the patent in 2014, and since then we have 5 working sites on mostly industrial, and we've come along in the last few years after getting our EU and US patent approved, and we've gone and worked with, in close collaboration with Wastewater, and we've proven this at full scale and demonstrated it. So to date now, we're in 2021, post-COVID, and we're ready, I suppose, to take, maybe, if I can be cheeky, and take the mantle from Nareda and say we're the ones for the next decade. It's anaerobic's decade, and let's get ourselves to net zero. So we're putting that challenge internally in our company, and we hope that a lot of the other anaerobic technologies will follow as well. So what is Ambirobic? How does it work? So it's simply, as I said, it's an upflow system. So you have your bugs in there and you pass your wastewater through it, and the BUD is taken out and it's converted to biogas. So we have BUD and TSS removal. So how much? So 80% BUD removal, 60% TSS. So that's what happens. So it's converted, and we then take the biogas out. So of course then you have the biogas for use 100% on site. So if you have a digester there, you just plug it in to your boiler immediately. And it works at low temperature. So ambient temperatures, whatever comes in, and I'll show you an example in a little while of it working between all the way down to 0 in some cases, but 4 degrees to 15 degrees on average. So how does it do it? What is the nut that was cracked? So it's twofold, and I suppose let me talk you through it here. It's an anaerobic filter section, which we have here. So this holds the bugs as a biofilter, and then it also works by retaining our bugs here. So they evolve and they evolve and they evolve, and then we also have a polishing filter here. And secondly, as I said, which is the driving force behind any biological system, is the bugs. We know who's there. There's been 20 years of sequencing, of research, so we're consistently monitoring them. And even on our systems, we take them out once a month, we send them to the lab, and we check who's there and what they're doing. So they work, and they work well at that temperature. So between the two of them, we work and we remove our BOD to biogas. And critically, as I've said before, that is not sludge. And we do that without low energy. So there's nothing else happening in that reactor, only biology. So we don't have any extra sparging, we don't have anything like that. It's a passive system. We just pass our wastewater through it, and we recirculate lightly at a light upflow. So I suppose, how does this fit? It's the core of the net zero process going forward. So you have 2 options there. Obviously, if you're going to river, you'll need to have pretty stringent NNP removal. And now a little bit of a change. If you're going to sea discharge, you'll only need BOD removal generally, unless you're going to somewhere a little bit more sensitive. So with Ambirobic, we offer for sea discharge, you can go straight into a sand and cloth filter and go straight out to discharge because the majority of your BOD is removed. With going on the more standard process flow, we will go in post-screen, you take out all your inerts, and in Welsh Water we worked with the standard 6mm screen, and you go into your ASP. And critically, of course, we work with a little bit of a bypass system to ensure that there's enough BOD for your NNP removal going down. So we'll go into that a little more detail. But ultimately, that comes down to you're reducing your BOD, going to your ASP. It's working more efficiently. Your nitrification, denitrification will be more efficient. We were talking a lot about BioP removal yesterday as well. You don't have any aeration on the system, and I suppose you have no membrane or it's a passive maintenance system within our tank. So it's been done. We've proven it, we've shown it, and how did we do this? So we went, as you can see, with Welsh Water, and this is a full-scale pilot system that treated 700 meters cubed a day. It was brought in on the back of a truck just before winter, I suppose, or in the middle of autumn, and we set it up within 2 weeks. So we have modularized everything. You can see there's a few containers. One's a bit of a boardroom. The second one is where everything is. It's that simple. We have 2 sets of pumps. We have a recirculation pump, and we have an influent pump. And obviously the influent can be removed if you have a bit of gravity flow. That's not a problem. And we have an MCC panel with some instruments, pH and MLSS. But crucially, you can see it all fits in the tank. So there's very little extras. So the results that came off this were detailed. And we have significant automated sampling on there. They were reviewed by Welsh Water, reviewed by ourselves. And you can see in the red line the BOD that was coming in, and the green line was ourselves. So you can see very, very easily that we started off in autumn and summer, and then winter came, and it was a lovely wet Welsh winter. So I suppose I didn't say this was built wells in Wales. So for me, I had to Google it. Still do sometimes, really. But we then went into winter, and as you can see, there was significant infiltration, way more than we expected, way more than Welsh Water expected, to be quite honest, and it was a wet winter. So if you do have any questions, don't hesitate to get in touch. So what difference does it make? You know, we have all these utilities. How does it kick in for you? So ultimately, you have an upgrade, you have an increase in PE coming down the line. You're naturally going to think, right, I'm going to need next percentage more, and let's just do the same again. It works. Well, maybe we shouldn't. You know, you have high OPEX, aeration, you have no biogas unless you increase your digestion facilities, and then your sludge disposal is uncertain. I know back home in Ireland, there's a big worry now, is like, what happens if we're not allowed to put it on land? So, you know, this is where it comes in. We're not saying that aerobic is gone. Absolutely, you need nutrient removal, and there's some very, very nice technologies out there to do that more efficiently now. But let's do this a little bit better. So let's come in and let's give you the savings. Let's work, you know, be it ourselves or other anaerobic treatment technologies. But let's use these savings and use them to our benefit. So we'll come in and we'll put ourselves post-screen. You'll take the majority of the excess BOD. You'll have a bypass there to ensure that a certain percentage goes direct to your aeration system, and then you'll go forward with that. And that will give enough BOD to remove your NNP. 100% of the wastewater goes through your aeration still to remove that NNP, but not all of the BOD, just enough. So therefore, you will have BOD removal, you will have a little bit of biogas, but you'll have significantly less sludge. You'll have a more efficient system all round, and you'll have an upgraded modular system. So for example, for 10,000 PE, we have our module is 16 meters wide, 6 meters high, and we treat the wastewater at dry weather flow in 12 hours, all the way down to 4 hours treatment for dry weather flow ×3. So it's a nice, tidy system that can be put in with glass-lined steel tank pretty easily. And you know, you have no aeration, low energy. So just to give you a few high figures, I'm going to hand you back to Alan. If you have any questions, we're all around.
Yeah, we're virtually done now. Thanks for listening. Couple of slides that CapEx and OPEX, it's a massive saving. We've done some work on a European municipal estate to see, you know, what the CapEx and OPEX savings are. They're absolutely massive. You know, that's the percentage flow that we would take of the whole estate over 20 years. And you can see the kind of capex savings, and then the opex, it's just massive. On top of that, net zero carbon and the tons that you save is just absolutely enormous. So thank you for listening, and we're here for 5 minutes, I think, and we're also in the hall. And there's our contact details. Thank you very much.
Thanks both. As someone who saw the technology a few years ago at a relatively early stage, fantastic to see it having developed to the stage you're at now. So yeah, congratulations on that. I'm going to take the chair's prerogative and ask a quick question, if you don't mind. As a big fan of anaerobic treatment, have you thought about, and if so, what are your proposed solutions to the dissolved methane? So, cold temperature, one of the issues is that a lot more of the methane is in the dissolved phase, and if I understood correctly, your flow sheet is post-treatment, say through an ASP. Yeah. Aren't you risking stripping a lot of that methane out?
Yeah, absolutely. It's something that we're kind of working with consistently. So first things first, our filter allows the methane to break away. So we've compared to standard UASBs, and we definitely have more in the gas phase than normal. But then we can also go at much lower temperatures than some UASBs, so it is tricky. So ultimately we remove the biogas, and you just can't have methane going into the atmosphere these days. So, you know, vacuum degassing is something that we're looking at as probably the priority and the easiest way of doing it. So you collect your effluent just in a simple tank afterwards, and you strip the last of the methane out, and it goes and it joins the rest of your flow. So that's the simplest solution. But then you also, you know, if you really need to clean your wastewater for reuse or something, you can use membranes, and that will give you the extra cleaning, but also remove your biogas. But simpler is better, and so we're leaning towards vacuum degassing, but we'll work with the client on it, absolutely. Yeah.
Thank you. There's a question from Hopin, a couple actually. How do you go about nutrient removal, and how do you foresee removing emerging contaminants?
So nutrient removal, we stick with what's there on site. So nutrients need to be removed, and we'll work with the client. So what we do, priority one, is to make sure that ASP that's on site or inbuilt with trickling filters has enough nutrients to remove the NP, like they've been doing for probably the 25 years before we arrive on site. So that's the main thing, and we remove the excess BOD then, and we design our system around that. How much flow do we take? It's due to that amount. Emerging contaminants, fascinating question. A lot pointing towards using the anaerobic system, and then going into aerobic is actually even more powerful than aerobic itself, because the anaerobic process can break down pharmaceuticals a little bit differently. It's always on the top of my list. I'm bugging Alan for a few bob to try and test it. So the next time we're on a big site, we'll definitely come back with a paper on that. Yeah.
Brilliant. One other quick question, then I'll hand to the floor. So what levels of operator input or interface are required to run the plant?
Limited enough. So we have it all automated. So built wells, we ran it, I suppose we were checking in a little bit more because it was a pilot, but ultimately it came back to a laptop. We had an operator there once a day checking in on all the systems, but mainly it was checking on the screen like they would be doing day to day. So it operates, and it will change from dry weather flows naturally. We use different probes to do that, so it's very limited.
Yeah. Crucially, it's an automated process. There's no moving parts inside the reactor. Very little maintenance. Hardly any inorganic sludge build-up at the bottom of the reactor for this trial, and on our industrial units that we've got, which treat massive COD levels. Very little maintenance. It simply is a reactor vessel with upflow. And crucially, the biofilter, it doesn't block. It's like a granular structure that the biomass cultures on, and that's what holds the biomass in, does the final bit of filtration and polishing and producing gas. it's really low maintenance, and it all adds to the numbers that we flashed up on the screen as well.
Thanks, Alan. Right, I shall hand to the floor. I think I saw a question here.
Hello, Mamata V from Southern Water. Thank you. Very interesting presentation. It's a closed system. What about shock loads or souring of the digester? Have you all experienced that? And what's your...
So the difference between us and your sludge treatment is we're not really organically limited. So I mean, you're putting in sludge, which is heavy and organic, so you have to watch your VFAs, you have to make sure your alkalinity is okay. Here you're putting in very dilute brown water.
Yeah.
So the sludge, there's more than enough sludge to do the work on that. So shock loads would be an emergency situation whereby someone puts in sludge into the system, a totally different, incorrect. It's not a shock load organically. It's the volume that we must limit and just make sure that you don't just let it go freely into it. But that's valves and pipes and everything like that. So
yeah, we had an incident on one of our industrial reactors where massive amount of cleaning chemicals went into the reactor, and our seed sludge, it's commonly available. You get it within a week, and as long as there's some activity still there, you either wait for it to grow back, which obviously you might not be able to, or you put some new seed sludge in. But it's very, very robust. In municipal wastewaters, for a week in Wales, it treated BOD down at 0 to 4 degrees, and the bugs just stayed alive, and then once it warmed up, just became active again. So it's very robust.
Is there a minimal seeding period then?
Right.
Yeah, we have a commissioning period, just about 6 weeks. But ultimately, seeding, we put the bugs in as they are. We don't grow them out of nowhere. We put them in and they acclimatise. But we're testing them in the lab, and we do a monthly test of activity. So we know what bugs we're putting in there, and we can merge different strains and stuff. That's fine.
Great. So I'm trying to balance off.
Yeah, balance time.
Considerable interest in time, but AJ had his hand up. So last question from AJ.
Awesome technology, guys. Thanks for sharing the details there. We've got a lot of sunk assets, particularly primary treatment, conventional. Is it possible to retrofit the technology? That's the first question. And then, sorry, Pete, saying cheekily, secondly, you mentioned that you use 6 mil screening, and that's not been a problem, but I do know that all wastewater treatment assets that we tend to have usually have quite poor screening, and there's a tendency for a lot of fugitive screenings to end up elsewhere in the system. I don't know, did you experience that, or are you thinking about better protection up front?
Yes. So in terms of retrofit, you've seen the images of the reactor at Built Wells. It's a small one, and on our industrial plants, it's low land take. It comes on the back of a wagon. If it was a 10,000 PE plant, it'd be like a Perma-Store tank with a roof. It's very simple. So most of the work is just simple slabs, associated pipe work and M&E, and it turns up on the back of a wagon. So the disruption, compared with the big concrete ASP tanks that we've been building for hundreds of years, it's minimal, absolutely minimal. Effectively, it's package, by its very nature, turns up on the back of a wagon. In terms of the influent, it needs screening. If anything gets in, you can see around the bottom of this that there's access, so that you can clean it out. But as with many processes, you'd want grit screen, and you wouldn't want rags through it.
No, thank you very much.
I think just a quick addition, and I suppose on the retrofit, they've begun, Wastewater are leading it a little bit, and the tanks, it is a tank that's, the aspect ratio is changeable, so we can use old concrete tanks if needs be, but the easier modular solution is definitely going forward.
We've asked the market, concrete, precast concrete, this is stainless steel because it's a small plant and it was the most appropriate. Most of the municipal water companies want the least carbon. When you look at it, it's glass-lined steel tanks.
We bet.
Oh, hydraulics, right.
It's pretty easy, to be honest.
Can I suggest, because I know there are loads of other questions that you pick up outside, I better move on to the next presentation. Yeah. Thanks very much, guys. So our final presenter of this session is Phil Longhurst. Phil's joining us virtually, so I'm hoping you're there, Phil, and I'll hand over straight to you. Can you hear us, Phil?
Great, thanks everybody. Hope you can hear me okay. Sorry to be joining you online. I hoped I'd escape from the house eventually, but factors got in the way. So I want to, in this presentation, just briefly kind of scope where we are with greenhouse gas emissions from wastewater treatment processes and look at the origin of this issue in our understanding, the drivers for concern, and also where our priorities are for understanding in the future. So the subject of greenhouse gases and achieving net zero is often referred to, and yet the focus on measurement and our understanding of process variability and how this relates to attempts to offset these emissions is relatively poor. So in the perhaps in the tradition of great investigations, what I've done is structure this to think of the a sequence of the 5 W's: who's concerned about greenhouse gases, and the drivers for this concern, the focus of greenhouse gases from wastewater treatment, where emissions occur, and then what influences take place, so when these take place, and perhaps most importantly, why it is that our understanding is limited at the process scale and what could be done to address this. So if we sort of take a big step back and think of where greenhouse gases and the focus on greenhouse gases started, the international consensus and agreement that was reached in Kyoto back in '97, and what we're looking for in terms of future changes this November, really sets out the framework for limits and agreed limits to achieve the global targets. That's then translated into our national understanding of emissions by sector to define limits and prioritise policy interventions. And that's really reflected by the UK's Climate Change Committee and measurements and principles and methods applied, for example, by the National Atmospheric Emissions Inventory. But this then comes back to operators having policies that have direct financial impact on their business, the way they operate, the way they invest, their capital infrastructure, and the interest of consumers, so that both their investment, their environmental, social and government investment pathways, as well as community and users of those services, so represented by the whole cross-section of interests about climate change. Now, initially, the drivers for the climate change agreement were, the drivers for corporate carbon footprint were a synthesis of the climate change agreements, emissions covered by the carbon reduction commitments, and emissions covered by the EU trading scheme. And those priorities for control were set out in the first climate change agreements in Kyoto moving forwards. It then developed into emissions trading scheme alongside the OU, carbon reduction commitments, which were dropped in 2007, initially promoting energy efficiency, which then progressed onto a series of climate acts. And then as the CRC was withdrawn in 2010, this overlapped to a focus on industry, sector and specific targets. And where we are now in many countries is really a target which is driven by taxation on emissions in some form. And ultimately this means we have to adopt a set of emission factors for specific processes. And in the UK, the current approach for wastewater treatment is the Carbon Accounting Workbook. This is developed by UK Water Industry Research, and it uses an extensive spreadsheet for defined processes and loading rates, typically nitrogen. Alternatively, the IPPC set out a three-stage approach which seeks to prioritise the accuracy of emission factors at the local site, then if not possible for site-specific data, and then if not possible for global emission factors. Excuse me. This approach is useful in tailoring site-specific values. However, it's dependent upon reliable measurement, as all of these factors are. But measurement is proving to be tricky. So if we consider what the focus of emissions are in wastewater treatment overall, there's 6 greenhouse gases defined under the initial protocol agreement because of their dominance in CO2 equivalent impact. So we refer to these as CO2 equivalents because it's effectively saying what 1 million metric tons of a gas would be in equivalent harm or global warming potential to carbon dioxide. And we use kind of as a rule of thumb factors like 25, or you'll hear variations of this, but from 21 to 25 and so on for methane, and just under 300 for nitrous oxide. What's important to recognise is that these factors are trying to reflect the impact over 100 years on average for some gases, and others an infinite amount. So for example, if we think of methane as CO2 25 times equivalent over 100 years, it's actually 80 times, roughly 80 times worse than CO2 in the first 20 years. So if we can control methane at an early stage, we have a real opportunity, significant opportunity to make big reductions. And it's the eventual oxidation of methane over the 100 years that results in this lower value. Whereas you can see with nitrous oxide, this is a gas which really doesn't break down in the atmosphere to any significant rate. So that 298 is impactful in terms of global warming potential right from the outset. So where do different emissions occur on the treatment works? Well, understanding where methane and N2O emissions occur in the works is a priority in terms of where it comes from. The wastewater treatment process applies physical, biological and chemical treatment methods at each stage, and the rate of biological activity and oxygen concentration influences emissions. As we've heard previously from really helpful talks, anaerobic conditions are dominated by methane and CO2 emissions, whereas biological processes with changing levels of aeration, such as trickling filters, which were discussed before, release high quantities of nitrous oxide. And then we have to consider the shift along the process between aerobic and anaerobic states, both within the liquid and sludge material within the process. So examples of this can include sludge levels in tank, sludge treatment, biosolids, as well as suspended solids in the process. So what do we know and what's understood and what's not known? So we're trying to set out our understanding of the process. If we take a fixed emission factor approach, that becomes quite straightforward to apply if we can rely on it, i.e. what we understand and have data on compared to what is unknown. So if we look at the current research, this provides a broad range of site-specific examples of data, where some key influences such as nitrification and denitrification within a process has been recorded. However, in pretty well all cases of the reported studies, because sampling is costly and time limited, variation over season, variation over the day, and variation within the process itself is poor. And this leaves our determination of greenhouse gases, greenhouse gas emissions using fixed emission rates, problematic in two ways. Firstly, the fixed rates don't inform us how to manage the process. And secondly, thinking back to our global and national and international, local, national and international priorities, fixed rates provide no incentive or opportunity to reduce greenhouse gas charging, as our priorities have moved in policy terms to taxing emissions from processes. So we can see here on the left-hand side of the scale, we've got a lot of information about data, but our understanding of relationships is relatively poor. So let's take an example of this where we look at seasonal variation. If we look at some of these examples, just how much variation does occur. This, hopefully you can see this, but relatively small chart shows seasonal variation from influent organic loads. So this is adjusting for temperature, but the chart is effectively showing in kilograms of nitrous oxide per day, a range from less than 50 to over 400 across 1 year, across a 2-year period. So those huge differences in process loading due to nitrogen. Whereas in the chart below, if we look at diurnal variation, so throughout the day, if we look at dissolved oxygen alongside the release of methane, we can see peaks and lows from as high as 20 grams of methane per hour to as low as 2 grams of methane per hour within 6 to 8 hours of the same day. This chart shows 3 different sites across Japan, looking at the variability of methane emissions between the processes. And these are different process units compared for 3 sites. The A STP is Akyu, the H STP is Hirasegawa, and the K STP is Kamiagari. And this is an example of 3 wastewater treatments showing significant variations in methane. The GC and OD is a grit chamber. The second has oxic tanks containing free molecular oxygen, as well alongside anoxic environment. And then there's primary sedimentation and final sedimentation tanks referred to in a 3rd site. But what we can see in the boxes at the top is differences from 420.5 milligrams of methane per cubic meter down to 117. So a difference of 4 to 5 times between similar influence on different sites, just by process design. And if we think, okay, we've got the process design right, we could begin to understand, well, what might happen within the process to create more problems. So if we then look at individual processes, we can see that depending on the location within the unit, well, in this case, 2 lanes, the darker blue and the lighter blue, lane 1 and lane 2, we can see a plot of the temperature variation, but the emissions from those 2 lanes is hugely different between the dark blue and the light blue. So this site in Germany has variations of more than 5 times detected simultaneously on the same site. So clearly the site operation, mixing and aeration locations, local residence time and dead corners within the site all have the potential to greatly influence emissions. Excuse me. Lastly, if we think of, in terms of N2O measured, the distribution of inorganic nitrogen species, so distribution of N2O and dissolved oxygen in the water from different sampling points at the wastewater treatment process, for a German site in this case, shows that N2O is production is closely linked to oxygen concentration, and this can be a very localized phenomena. So here we can see from 0.115 to 0.176 ppm, high variation dissolved in nitrous oxide across the nitrification and denitrification process. So again, significant differences within the same process. And then if we were to look at a review of 50, in this case, 54 studies across a time period from 1995 to 2019, it shows the range of variation at different scales for pilot plant with effectively an 80-person population equivalent to a 1 million population equivalent, showing a variation from 1,000th of a percent for 25.3% total nitrogen to as low as 0.005%, with no significant difference in total nitrogen. So here this looks like process scale and properties of the scaling up of the process influencing emissions. What we can see from sewage treatment works is that, for example, in sequencing, what we recognise across the research is that there are a number of influences on emissions from activated sludge. We've showed daily, seasonal variation, that carbon-nitrogen ratios are important, managing the denitrification process, and in addition, understanding how to manage levels of dissolved oxygen and the dispersion of that across the site, and particularly where we've got, for example, sequencing processes like batch reactors, where process stages have potential for changing phases in emission. And lastly, there are conditions which may be reducing the risk of methane on the one hand, whilst exacerbating nitrous oxide release on the other. And perhaps, I was going to say perhaps most surprising of all, but recognising the earlier talk made this very point, that when we consider trickling filters, they can have a significant contribution to emissions in terms of nitrous oxide. This is both because of the process of ammonia being treated in the trickling filter, but also the very large surface area for relatively small emission rates means that the total mass of emissions becomes very high. So clearly it's not straightforward to try and understand this, but it's a priority to reduce these emissions. The impacts are significant. So therefore the sampling and the strategy we take to approaching this need to reflect both our understanding at the micro level to improve our understanding of the process, as well as understanding at the macro and site emission level. Ultimately, we want to get to inform and manage our sites to address national emissions on the top right hand of this diagram by Henson. But we can only do that if we understand what the properties are of emission from the processes collectively on the site, how they emitted and disperse, and from process studies that look at the individual units and the relationship of one unit to another. And ultimately this has an effect on how we manage inputs to the site and the way we spend money to invest and control these processes. So there's a range of sampling methods at local scale. Here's a couple of examples. Fourier FTIR, Fourier transform infrared spectroscopy, and cavity ring down spectroscopy, for where we can measure at local rate emissions of gases. We can also use N2O probe sensors to look at dissolved nitrogen in the liquid, as well as headspace emissions, nitrous oxide in the liquid, sorry. And we can use flux hoods or chambers where we can pass air through the chamber and look at the accumulated emission to give us a flux rate. So in situ, these would look something like this, where you have a floating hood and you'll be passing air through the process and looking at the accumulated emission and then sampling from there. And here's an illustration of the trickling filter sampling method, where we take a section of that filter away and place a headspace monitor directly within the filter to try and understand emissions from the filter bed. Ultimately, we need to develop a strategy, a management plan that allows us to understand the different roles that we can use data from emissions to control the data throughout its life cycle and ensure the data quality we get from one study can be compared to another. And this process is starting to build, certainly in the UK and across Europe, where data is becoming shared more commonly, and the influences on the process and the way that that's recorded is becoming recorded better. So this collection of, if you like, site metadata, what the process changes are, the maintenance, the process type, and the network changes are all improving. And in turn, this maximizes the use of data and secures sharing and transparency in the analysis. Finally, this would then get us to the point where we begin to understand the relationships for improved model building, so we can predict, manage, and control. And the opportunity to then start to use artificial intelligence to build applications to accelerate development of understanding these relationships. This will help us then develop future scenarios which we have to look at in two forms. One is the change that we can expect and are already observing from climate change. So we're seeking to mitigate climate change, but the impacts are already upon us in terms of increased sewage strength from low flows, dry weather, as well as surge flows from intense weather, increases in surge storm flows. And lastly, as we're experiencing right now, changes in workplace and city design and layout. So everything from home working to property development and reductions in combined sewers, local treatment processes, and differences in high strength and low flow of wastewaters. So thanks very much for listening. Welcome your questions.
Thank you, Phil. So, yeah, like Ellen's earlier presentation, a really clear summary of the challenge that faces us with process emissions. But yeah, you know, the importance of monitoring came through loud and clear there. Thanks, Phil, and some of the techniques that we can do that. So I won't keep you from your teas and coffees for too long, but time for a couple of quick questions. Oh, is Phil still there?
Yep, sure.
Oh, yeah,
yep.
Brilliant.
Yeah, okay.
If I start, Phil, could I... this might not be an easy one to answer, but how far do you think we can go through better control and maybe digital twins and making the most of our existing assets, and how much and what proportion of the challenge will need to be new assets, new technologies, covering tanks, etc.?
That's a great question. Probably one I'd like to ask you as well, actually, but perhaps over coffee sometime. I think there's two stages. I think we have a wealth of data that's currently being collected, but we're not joining that data up. And I think that has potential with targeted sampling and measurement programs, which are being designed to then start to improve our real understanding of process performance in terms of N2O and methane. And I think that's in the first stage, that's going to be very significant in terms of managing existing assets. It then comes to a point where we then really need to consider seriously how much we rely on relatively low energy input processes, for example, biological processes, to do the job that we've been relying on to date, which is energy saving and relatively low energy costs, therefore, and how we then might move to other processes, physical processes, or other forms of chemical processes where we separate out components that we know are causing a problem. And I think we'd see that as a new phase of asset design and development, and really a phase change, a future phase change in wastewater treatment.
Thank you, Phil. So if there's no more questions, I'll call it to a close there, but can I just thank all the speakers once again for a fascinating session.
Welcome back all. And I should thank Aqua Enviro really for allowing me to chair the previous session, which is the first half of my new job title, and this section, which is the second half. So this is all about circular economy, a subject close to my heart. And it gives me great pleasure to introduce Steve Palmer, another face and highly respected person that many of you all know. And Steve's going to be talking about systems thinking. So over to you, Steve.
Morning, everybody. Hi. So just to get us in the right mood for going to lunch in a little while, and to also move on to the presentation after mine, which will also be about the circular economy and what we need to do to create a sustainable economy, which is key for all of us. I'll be talking about today systems analysis as part of systems thinking, and how systems analysis in the circular economy is key in providing solutions for circular economy interventions. So, what we'll do is take a journey through some developments that occurred in Stantec, have occurred over the past few years. We established several tools which had quite a widespread utility for looking at how systems work, and we've been very successful in applying them. And what I'll be talking about today is the origin of our systems analysis thinking, and how we've developed it from tools we originally developed for projects looking at things like operating efficiency, and then incorporating carbon, and looking holistically at how treatment systems worked. I'll then move on to how that led to us developing an idea called big picture. The idea of big picture is there's a lot of developments happening at the moment. There are some key developments in physics. Probably in our lifetimes, we'll see physics move to the point of reconciliation of the two key theories in physics. That's basically relativity and quantum mechanics. Now, put that to one side, but it does have implications for what we're looking at here today, and we're going to take a little sidestep through physics and the most recent development in physics to look at the lessons that has for us in terms of how we make decisions, and particularly how we understand how important information and the use of information is. We'll then look at how that can be developed, and taking those principles forward could be developed into giving economics something it has lacked to date, which is a physical platform for looking at economic activity. And then we'll use a case study of that in wastewater treatment. So we started from a background in Stantec where we developed tools that had a widespread utility, that were looking at asset resilience, operational efficiency, operating cost. We used these tools for testing new technologies. They were very successful. And the question we started to ask ourselves is, why are these things so successful? What's behind it? What is it that we're using here that gives us such depth and breadth in our analysis? And it was basically because we were analysing systems, and systems analysis is a very flexible approach. When you're looking at analysing a system, it's very flexible because you can define a system boundary, but a system itself is always defined within an environment, and once you define the system, you start to look at key factors like its initial conditions, and how it can evolve and change and go through a process of change as a result of its physical properties changing. Very basic systems analysis principles give us a good idea of how important the management of information is. So, for example, if we take the same system, the simplest possible definition, we have a system, we've defined its boundary, we have defined an environment for it. If we have no data at all, we can't do anything. If we have no data, we have no information. Simplest, obvious outcome. But then, if our data has an analytical flaw, or if our data has a flaw in terms of the measurement, if we've got measurement error, we end up with an inaccurate outcome. So our system analysis will be an inaccurate representation of what's happening. We have misinformation. And obviously misinformation leads to erroneous outcomes, stranded assets, bad investment. Equally, if we don't have enough information, or if the information we have if we don't have very much information, we tend to have to deal with very high variability. So if we also lack information, we can be in a system where we can end up with a systems analysis where we're very uncertain about what our system is and what its system boundaries are. And again, that is an outcome that we need to manage and understand when we carry out a systems analysis. So when we're looking at systems and we're looking at information, and particularly in big data analysis, the risk of misinformation creeping in, we have to be very careful that the rules that we're using are broadly applicable and allow us to understand physically how our systems should be behaving so that we can have a weather eye out for where mistakes might develop. So when we looked at what we'd been doing in Stantec and we looked at the success of our systems analysis in terms of the tools we'd previously developed, one thing stood out. What we were using were the laws of thermodynamics. So we're going to take a brief tour through physics now, but we're also going to look at where physics is going at the moment, where it's up to in state of the art, because it has some important outcomes for us. So these are some concepts we're familiar with. First law of thermodynamics is about energy, and it's about energy passing in and out of a system. And that results in changes in the system's internal energy, but energy is also a conserved quantity. Energy is a primary physical quantity, something that's very key to everything that we look at. When we move to the second law, we can start to see what the consequences are for changes in states and how energy changes are related to changes of state, physical changes in the state. So, as a result of physical change within the state, the energy required to change the state results in a change in the state that we call entropy. Entropy is not a very well understood concept, and one of the things I'll do today is provide a fresh definition of entropy that gives us a better idea of what entropy actually is, because it's been misunderstood for some time. It's often described as a measure of disorder and order. It's not, and it never has been. There's a reason why that misinterpretation is applied, but basically, in classical thermodynamic terms, the kind of terms we're looking at now, entropy is about energy dissipation, transfer of energy. However, there's another aspect to the second law that's not often explored, and it's been the subject of a lot of advances in quantum physics recently. And that's that physical information within the system is related to the exergy in the system and the energy background of a system. So how's information related to this? Because we're looking at everything being energy, when in actual fact, relativity gives us the answer. E equals mc squared, mass-energy equivalence. Ultimately, matter and energy, we're talking about distribution of energy and forms of energy. And what we'll see is that when energy redistributes itself, it's redistributing itself into physical structures. And that affects everything that we do and everything that happens around us. So this is a very superficial, quick tour through quantum physics, but basically quantum physics is about energy and how energy change occurs at the quantum level, how discrete packets of energy result in physical change. Classically defined back in 1926 by Erwin Schrödinger's wave function, this definition, which represents an energy distribution and how it evolves over time, creates several paradoxes. For example, what happens is that the state can be observed to occur simultaneously in two conditions. So we can observe an outcome either in the form of a particle or a wave. And until a measurement is made, we either observe a particle or a wave. This doesn't seem like our real world. It doesn't seem what actually happens. But there is an explanation for it. And part of it lies in Heisenberg's uncertainty principle, which is what happens at the quantum level is purely random. It's purely stochastic. So when we're looking at quantum systems, what we're looking at is random variation and how that random variation can occur. And part of that is captured in Heisenberg's uncertainty principle. So when, for example, we look at complementary variables, an example is position and momentum, on a quantum level, we cannot both determine position and momentum at the same time. And that creates another factor, another paradox called non-locality. So when we're looking at quantum systems interacting, interactions can create information transfer, entanglement between systems. Entanglement means systems can interact and remain linked through the correlations of their interaction. Again, not something we're used to dealing with in how we think about the real world. Very recently, there's a range of 4 principal theories in physics relating to quantum physics, but the key theory that seems to be gathering momentum, a slight pun there in sort of physical terms, but the key theory that seems to be gathering the most support in terms of the recent developments and experimentation is decoherence. So the explanation for how quantum systems emerge into the real world is that a system decoheres as a result from a quantum state fluctuation, from a stochastic, a random change. One state emerges in the real world as a result of a quantum system decohering. The mechanism for decoherence is that something has to happen to make the system collapse. And traditionally in quantum physics that had been ascribed to the act of observation. But this happens anyway. There doesn't have to be an observer there. So that is a major challenge to decoherence. But we now have an answer to that challenge. What causes the system to change is the environment and its interaction with the environment. So at the most basic level in which reality emerges, physical reality emerges from quantum level physical systems, what we're looking at is basically physical information and how physical information leads to decoherence. So the environment is providing an interaction that allows physical states to decohere. So, although the behavior we're dealing with is purely random and stochastic, and we have information system behavior being observed in physical systems, it's actually now telling us, giving us an understanding of what's happening at the quantum level. What we see happening now, what's beginning to be realized in quantum mechanics, is that information is actually acting in a physical way, and information has consequences for how physical systems interact. Energy is displacing itself, energy is redistributing into physical structures, and that has an outcome. If we look at entropy now as a process, there are 2 sides to entropy. When we look at information, the last point on the last slide was talking about, in information theory, entropy being a measure of missing information. That's also a physical aspect of physical behavior, because when we look at energy redistributing itself into physical structures, there are information changes that occur. So what we're looking at when information redistributes itself is effectively statistical mechanics, the statistical mechanics of information. Information is a physical aspect of how physical systems occur. has some very interesting outcomes when you redefine entropy as a process. Because if you redefine entropy as a process, you look at both sides of this transformation. You're looking at the fact that energy is redistributing itself into physical structures, and at the same time, those physical structures are a representation of a change in information, but also a spread of information between structures. And the correlations, the statistical correlations that arise from that, lead to missing information. So missing information is entropy, and it is entropy at the quantum level. It's real, it's physical. If we take that redefinition of entropy, we can then start to see some very interesting things. If we then consider how energy dissipates, diversity in physical structures provides opportunities for energy dispersal, energy redistribution. Complexity of physical structures does something different. It increases the intensity of energy dissipation. So why is all that important? Because economics obviously doesn't deal with any of this, but there's an underlying key message in this, and that is, at the deep physical level, information has consequences for how much energy and activity can be obtained from physical state changes. So when we start to look at the big picture and what's happening in the world, what we're dealing with, if we take note of what physics now has to tell us, is that information and the utilization of information has a major impact on physical intensity, on the physical intensity of any physical processes. So what's intensity about when we look at our economy and we look at the global economy? Well, we can see the result there partly. We can see the result of the human population utilizing information to maximize its returns in terms of energy and resources, and also maximizing knowledge to maximize our longevity, to maximize our resistance to disease and our ability to manage disease. That utilization of information that has driven our populations to rise exponentially is also the same explanation for why the global per capita, our average consumption and our average productivity has risen exponentially. It's about returns on information. Returns on information and utilization of information make biology something different to chemistry. So now we have something quite profound. We have a new definition for life and biology. All that biology is a form of chemistry that has a chemical memory, that also can secure enough resources and energy to maintain that chemical memory. Why is memory important? Because memory allows you to maximize resources and maximize return from resources. But that also means that kind of learning system, which all biological organisms are, tend to be associated with very intensive energy dissipation and very intensive resource dissipation. And the more we utilize information, the more intense it is, which is why we are where we are now. Because if we consider our basic thermodynamics and we consider what can happen in a wastewater treatment plant, and we draw the systems diagram for a wastewater treatment plant, what we can see is how we utilize energy, materials to carry out the wastewater treatment function, but thermodynamically the system has no option but to generate wastes. All systems, any system will generate wastes. It's a consequence of the second law. Now those wastes, we're familiar with some of them. They include sludge, sewage sludge as an example, other residuals such as grit, but they also include wastes like greenhouse gases, which are a major issue at the moment because of climate change. So where we have highly productive systems, where we have high productivity in the economy, where we have high productivity in wastewater treatment, we also have intense waste production or intense waste production. So what then happens when we move on to look at a wastewater treatment system of systems So here we're looking at an asset base across a theoretical water company. Across the asset base, what we're seeing is on the left-hand side of the graph, we're seeing the cost, the unit cost of treatment, the cost per PE. The cost is very high for small plants because small plants lack physical efficiencies of scale. There's not the same opportunity to maximize productivity. Productivity is an intensity function, a physical intensity function. On larger plants, we have those economies of scale. Productivity is good. We have a low cost to serve on our largest sewage treatment plants. We see the same thing when we look at solution development and the cost of capital, and the same reasons sit behind it in terms of developing solutions and how it's done. If we look at that range of assets and technologies that we might deploy, we see exactly the same pattern. Productivity on the technologies and the technology application. Some technologies work well in some applications and not well in others. Some technologies are inherently quite expensive in terms of their energy demands, and that's what we're seeing in this graph. And if we look at sludge treatment, we see a very similar outcome. The largest STCs and the largest sewage treatment works give the lowest cost to serve, give us the best returns across the asset base. If we look at what's happened over the last few years in terms of emissions and how we have dealt with emissions, what we're seeing is that we are bringing down scope 2 emissions, the electricity associated emissions, because we've done a lot of investment in renewable energy generation and in the and in energy efficiency measures. So what we're left with is the orange line, process emissions, now being a predominant part of the issue we're facing when we're trying to reduce our greenhouse gas emissions. So the investments that we've made have brought us down to a point where we have a more recalcitrant set of emissions to deal with, the ones that are coming from treatment itself. And where are these the strongest? This graph is the inverse of the productivity graph. It's the inverse of the cost per asset graph, and the reason for that is intensity. So we're looking at the downstream consequence of high productivity. High treatment productivity means high production of greenhouse gases. So the greenhouse gases are the highest, the greenhouse gas yield intensities are the highest at the largest wastewater treatment plants. And when we look at how we deal with bioresources and how we start to develop the sludge business and talk to Ofwat about that, we also see issues with regards to transport and issues with regards to treatment. For most wastewater treatment companies, there are differences in the demographics and geographic position that wastewater companies have to deal with. They inherit that, they don't control it. Ofwat doesn't make allowance for that. When you look at transport, the power law relationship there, the power law relationship in treatment systems, they're all aspects of physical quantities happening in our assets. These are all physical effects. In terms of the transport, the people with the highest transport costs are the ones with the smallest populations that are most scattered. The water companies that are in that position don't control that, and it puts them in a different playing field in terms of their costs. Both for transport, it affects treatment, it also affects disposal, because your disposal route principally at the moment goes through sludge to land, which keeps costs low, and it's a beneficial reuse. So just to conclude, one of the issues we have today is that economics and also the regulator are not looking holistically enough at the risks and problems that different water companies face. If you take a deeper approach and you have an understanding of how information and use of information and how physical scale and productivity as a physical mechanism affects assets, you can get a truer picture of the different pressures that are being levied, that are being applied to different water companies. So, in summary, we're not all on the same playing field as different water companies, and some of the aspects of those differences need to be looked at. The solutions we all need to drive out to produce sustainable water treatment are circular economy solutions. And the circular economy is about resource efficiency. We need to be taking a holistic view and upgrading our strategies, things like energy and sludge policy and sludge policy development and TOTEX, they're all interrelated. We need to understand how it all fits together. Thanks for your time.
Thanks very much, Steve. Yeah, really thought-provoking stuff and illustrates the need to not look at things in isolation, but ourselves as water companies and regulators to use systems thinking and proper system analysis. So, any questions from the floor? And I'll check. I don't think I've got any on the Narinda.
Steve, it's a question around, so originally we used to have special factors workshops with many clients to try and tease out where there were special reasons why additional funding could be sought from Ofwat. Could you comment on, so my understanding is that process no longer exists?
It's
Really?
another example of something that we had that it's a shame it's gone, because again, I thought that was always a correcting mechanism that made up for some of these differences and the differences in the playing fields that the different water companies are on. And something like that, there should be some mechanism like that that allows us as an industry to inform Ofwat of where these differences sit, the significance of them, and how we can then help different water companies best respond in their own way to the key challenges of making water treatment and wastewater treatment sustainable.
And just on that, there is a mechanism, sorry, I'll come to you, delightfully called UMIs, which are unmodelled expenditure, so you can make a case for things that don't fit with the sort of with the regulatory models. But last question to Thea.
Hello, Thea Eakins-Coward from Industrial Phycology. A lot of the talks are saying how we need to talk more, we need to have more discussion, we need to be more holistic. What do you see the future being? How do we get to that point? Because we're saying we need it, but what's the next step beyond needing it? How do we actually get there?
Yeah, I think
I
think communication's key. I think part of the problem at the moment is to deal with climate change, the technologies are there. What needs to be done in economic terms is there. The problem is there's economic inertia because a lot of companies that have, say, got money sunk into fossil fuels, those are stranded assets. They don't want to move that out very quickly. All those kind of practical challenges have to be dealt with politically. The point I'm making is that we've got a political problem at the moment. So the barrier is really political. Political in terms of water industry. At board level, boards need to understand that their solutions from now on should all be based around circular economy approaches. The circular economy is resource efficiency. It brings you benefits. It brings you cost benefits. It brings you operating efficiency benefits. So it's not just about climate change. It's about that sustainability approach also delivering you a better business in business terms. So that can be communicated better to shareholders, hopefully, in future. As an industry, we need to have strategies, and we need strategies that are not just fixated around 5-year plans. We need to act now and urgently to meet what's our 2050 carbon targets. And we're already running late. The OBR, the Office of Budget Responsibility, showed that inaction on investment in climate change across the UK at the moment, in the UK economy, if we delay action on climate change just by a decade, our national debt will roughly treble. We're paying the cost for that every day, but it's also our children that are going to pick up the bill and their grandchildren. And I think we all need to think about that.
Brilliant. Thanks, Steve. So our final paper in the circular economy session before I hand over to Martin and the natural solutions is a really, really interesting technology and a great illustration of circular principles, circular thinking. I've had the pleasure of working with Peter for the last couple of years, and I shall hand over to you, Peter, to tell everybody about it.
That's very kind of you, Pete. Thanks very much. Good morning, everybody. Thank you for the opportunity of speaking here today. Basically, I'll be talking to you about how a particular class of fertilizer materials can be used as a conduit to return resources held in waste back into the economy. And I think it follows on very much from what the last speaker was saying, and also to take his lead slightly in stepping back into the fundamentals of how the energy works. The low energy systems end up with you lot. Now, there's a whole range of technologies that can reaggregate that energy, pass it back into the economy, where it can be refocused to deliver improved products again. And I think, again, we need to remember that this isn't just about recycling waste. There is an opportunity before us now to create new materials that are better and more efficient than the previous ones. And the great advantage that you guys have is that you hold a lot of the resources. Okay, so as I say, I'll be talking really about organo-mineral fertilizers. These are far more prevalent in Europe than they are in the UK, but they're very much a developing sector here. And interestingly, a lot of the resources that can be used to make those materials are held within the water industry. Now, organo-mineral fertilizers ultimately fulfill the same function as conventional fertilizers, and at the moment, they're the fastest expanding global product for the fertilizer sector. The reason for this is they can be applied as pelletized materials in the conventional way. They can be very much produced as standard products, mirroring in effect and formulation standard NPKs of conventional fertilizers. The key difference at the first level is that they tend to have organic contents of between 30 and 50%. The benefits of these fertilizers over their more conventional alternatives, the mineral ones that are established in the system at the moment, is that they're essentially less polluting. At a basic level, there's less NP and K runoff. And because of those reduced losses from the system, actually the need to apply basic nutrient loads is reduced significantly. Then there's a wider range of benefits that accrue to the products, are largely associated with the organic material being returned to the soil. So there's a whole range of quantifiable benefits that can be seen in the overall context of enhanced soil health. And going on to the larger picture of what people have been talking about today, they represent a clear opportunity to restore carbon to the soil, but also to reduce the energy inputs into industries that are conventionally producing those fertilizer materials at the moment. So in terms of scale, just looking at the UK conventional fertilizer business at the moment, we're using something like 3.5 million tonnes of fertilizer, of nitrogen applied fertilizer a year, 1.8 million tonnes of P, and 1.8 million tonnes of potash. Now, is it realistic to look at recovering those materials from within the waste industry? There's a whole raft of studies over the years that have highlighted possible potential of areas. Now, from within your own industry, it looks, and this is UK figures, it looks like there should be somewhere close to 2 million tonnes of nitrogen available. But also there's competing sources for you. So there's a lot of nitrogen available from within the AD waste treatment systems and also from within agriculture itself. P&K potential, again, those numbers are there so that you do hold sufficient resources to transform that industry. And you want to bear in mind it's essentially a very profitable one, but also a very carbon intensive one. So the other big advantage that you have is large quantities of partially digested organic material. And this is great stuff to return to the soil, as you all know, through current spreading. But if you present it in an improved form, you can make a real contribution to returning carbon to the soil, where it works in a lot of different ways, not least of all as a carbon sink. And when these stabilised materials go back to the soil, there's certainly a market in the UK for 12 million tonnes annually and probably more. And that's on a dry matter basis. But the challenge you've got is that, there's other people wanting to get into this area, the ag guys themselves, but also increasing the food waste people. So in simple terms, short-term numbers, these are conservative figures coming from the fertiliser industry themselves. So they see growth in the UK up to 1 million tonnes of OMF by 2030, so it's a £300 million market. The reason I put these up is not really to look at the financial side of this, although there is a significant point here. The big difference is that the big money will be in the carbon side. And certainly now, with methods of recognising that carbon value, both on 20 and 50-year sequestration schemes, where the prices of €52 are available in the market at the moment and are looking to increase, that's something that shouldn't be dismissed. And also on top of that, there's the whole range of avoidance characteristics that can be brought in. And I realise, having picked up from what people have been saying about quantifications of these things, the avoidance is always complicated. Actually, avoidance with OMFs is quite simple because it's a direct displacement of conventional fertiliser. So it's a relatively straightforward and clean one. How do we do this stuff? As Pete said, we've had the pleasure of working with Severn Trent for quite a while. We developed, and in fact, this is a pilot plant that's going through commissioning with Severn Trent at the moment. But we're based in Swindon. We're only a small business, 18 headcount now. Our background is in developing engineering processes that use carbon. And it so happens that one of them is a good, neat way of making fertiliser in a low energy and reduced carbon intensive way. Main sectors we're working in are wastewater, obviously, food and agriculture. We've got quite a lot of IP around this technology. And we've got deployment with Severn Trent coming along and others in the food treatment business. The technology itself is actually quite simple. I think the great thing is you have, from our point of view, whether it's the water industry or the AD waste people in food and agriculture, you're agglomerating resources in one place where we can pull them together, make them into a concentrated product, and then redistribute them properly into agriculture. Now, essentially, the system works on quite a simple basis, mainly on dewatered sludges being fed into this big unit on the left hand of the system above the automation and control unit. Works its way round the process where we add appropriate additional nutrients, either from recovered sources or from bagged ones if appropriate. And then finally, we add the nitrogen component to the system, which in our case is produced by, wherever possible, using captured ammonia, which we react with carbon dioxide to produce a bicarbonate, and then we go on to stabilise that further to make an ammonium nitrate material. So essentially we need the fibre materials. We can use the ammonia that's already held in those, where it's, and obviously in some cases that can be at quite high levels already, but we like to add additional ammonia to that for most of the fertiliser systems. We're stabilising that whole basic assembly with carbon dioxide, adding some extra nutrients to balance the formulation and give the farmer what they think they want, and produce a pelletised product at the end. Okay, so those systems can either be retrofitted or new build, as long as we got access to the biosolids, CO2, phosphorus and ammonia, which are obviously things that you have around in abundance. It's a relatively small system. We have different metrics, 500 meters squared for a basic unit with an output of around 10,000 tons. We've now moved on to the autumn category of this. We used to do this in tennis courts, but obviously we've now got football pitches, I see. The big thing about this is all the processes that we develop, and I think this again goes back to points made by the previous speaker, because you're taking advantage of essentially everybody else's effort that's been put into in energy terms into these systems, it is possible to build something, because it's a good product, that is actually profit generating. And certainly we see these units as being not a way of capturing a bit of carbon and offsetting a bit of CO2 and returning a bit of carbon to the soil, but very much as a profit generating unit, based on the resources that you and the other people like yourselves hold. And so we see returns on these units of around 13 to 15% IRR on a project related basis. Then there's the sort of cost-related things which you will actually know far more about than I do in terms of water reduction and transportation, which obviously will vary considerably across your sector. But it does give you this new revenue stream from the sale of the fertilizer. And I think the one thing you want to start thinking about here, and it's why I'm concentrating on these OMF materials, this isn't about upgrading sludge. This is about making better fertilizers. And you can charge proper money for those materials. People are charging for it, and quite frankly, at the moment, the biggest issue we have is being able to make the things quickly enough. So there is a real opportunity there. And then layered on top of that, there's the increasing opportunities that are being raised around carbon. Just a quick one looking at how this works outside your sector. So this is a waste facility that we're building with PepsiCo around the Walker's facility in Leicester. And essentially there we're recovering ammonia from a water treatment facility. That's being shipped in, unfortunately. But that ammonia is then used to capture CO2 combined with the AD waste from essentially the peelings of the the crisp manufacturing. We're boosting that with a little bit of P&K, some from recovered resources, others from bagged materials, and then producing a fertilizer which is actually going back to the PepsiCo supply chain. And I think the thing here is, we've been working, as I say, with Severn Trent for a while, but been working on this technology now for probably about 7 years. And what's interesting is the thing that has finally generated the sales is that the customers are demanding from the brands that they see zero carbon. Pepsi see value in that. They've come and said, how do we reduce carbon in our supply chain and do it, being American, at a profit? And so they're following this route, and certainly it's one that is going to be expanded in other sites across the country. Just going back a little bit to how well these materials work, as I say, we've been looking at them for the last 7 years or so. We were originally just looking for yield equivalence, and this slide relates to that, but it's very much we've had that independently assessed over the years. What we're actually seeing now is that and once we've got better at it and we're reducing the losses from the system, we're actually able to apply significantly less nutrient to the field and get the same yields as would normally be expected. And those not just in quantity, but also in quality of proteins as well and all that sort of thing. So that's very promising indeed. In the wider benefits to do with the actual use of CO2 within the process, but we're also seeing, and this was originally reported in this journal 3-4 years ago now, but particularly enhanced through new studies that have been carried out by Cranfield University in the last year about returning the carbon to the soil in a quantifiable way, helping the improved microbial activity, affecting the the moisture content of the soil, which leads on to reductions in runoff and volatilization of nutrients and that sort of thing. So again, going back to the points that people were making earlier about data being quantified, it's always difficult in biological systems, but it's not impossible. And we can see some real improvements there, so it's great. So all these benefits really are coming from the simple fact that we were incorporating CO2 in the process to start the stabilization of ammonia. And by stabilizing that ammonia, we were able to have a real quantified benefit and saleable value for that ammonia that's held in the AD products into the final product. And then also, because when we do our trick capturing the ammonia with the CO2, we end up with ammonium nitrate, but also we're co-precipitating chalk, which helps in the release of the nutrients into the soil in the long run. And again, that's improving the overall resource efficiency that we're getting from the nutrients themselves. And 2 minutes, okay, that's good, it's quick. So, and so it was all about fertilizer materials and how great they were with nutrients. Increasingly, let's all be aware, it's all about how important the carbon is. We're sort of cracking that nut in several ways. One, through the direct capture of CO2 within our process and the long-term storage of that CO2 in carbonate form, but also by stabilizing the organic material that's putting back into the soil. And the numbers here, there's all sorts of different metrics for this, but they have large-scale, meaningful effect on what is going on. And yeah, this is the mad Frenchman who flew around the world in a solar-powered plane, was kind enough to pick us as, I think we're number 273 on his solution list. So he's nearly, I think he's got 800 on now, so that's good. But I think, the time has come for a whole range of solutions that do cross boundaries within the sector to actually start delivering some goods. And they are there and they can be acted on straight away, and you can make money out of them. Okay, that's me done. Thank you.
Brilliant. Thanks very much, Peter. Straight to Steve.
That was fantastic. Thanks ever so much for that. I've just got three quick points. Hopefully to help you with what you're doing. Your carbon footprint. I mean, the harbour process is a nightmare, and obviously you're undercutting that in what you're doing. So on a sales point of view, that might be something just to put on the sales of your product, X% less than standard fertiliser.
I'm trying not to be too salesy in it. Basically, we reckon it is 90% less than conventionally produced fertiliser. And
The other thing with CO2 is that on some sites, on some sludge treatment centres, at the moment, there's a possibility, quite a few water companies are moving to upgrading their biogas. Upgrading their biogas often creates a carbon dioxide waste stream. So there could be a new source for carbon dioxide for you.
Oh, very much so. And it is one that's been pioneered by Severn Trent.
I'm
sure
Pete's got that covered already. Yeah. So I suspect that's not a new one. The other one is, it's a factor that's going to be moving in your favour. At the moment, there's discussions going on. The EA is looking at sludge regulations and disposal to land for biosolids. You do represent an alternative outlook for water companies processing their material that still would allow them to recover, sell a product, and be able to get minerals to land.
Yeah, and I think actually it's one of those things that I've spoken very much about fertilizer analogues, but what we can do, in really simple terms, we can do a high-end material that goes on in the spring, but what we can also do is be producing a lower-end high organic material which munches up lots of sludge. So you've got something that's 95% cake derived, essentially, that can be applied in either, in reality, the university, because it doesn't have the issues with water and spreading and all that stuff. But even if it had to be applied in a narrow window, you've got a slot where you can do it. But where its value in both terms of nutrients and carbon can be fully quantified. So yeah, that's very much there.
Because another part of that, one of the things I was driving at there is you sidestep the microplastics and some of the associated contaminants.
Yeah, well, you can do to some extent. So we've obviously got to be careful. At the moment, we're sport for choice because we've got a lot of very clean, particularly like somebody like Walker's Crisp. There's no plastic in it. It will be an increasing challenge to make sure the microplastics are as low as they need to be. Now, when we started off, we were working with Viridor on this, and they had a lot of plastic in products, and it is possible to get it down to appropriate levels, but only if you get value for the end product. There's, that's exactly. Yeah, thanks.
Great, and I think on microplastics, the other possibility is gasification and using biochar in the product. So maybe that would be the route. I'm really tight for time, and I don't want to eat into Martin's section because he'll. So could I ask? Would you mind, Peter, picking up? Because I'm sure there's loads of questions.
I'm not going anywhere just yet. So
perfect. If you can ask Peter directly, that would be appreciated.
Thank you.
So thank you, Pete, for chairing that. My name's Martin Jolly. I'll be chairing the next section, which is natural solutions. And the first speaker we've got is Matt Palmer from Severn Trent Water. So we'll go straight into that. Thanks.
Cool. Good afternoon, everyone. Thank you for inviting us to present, and hopefully this virtual presentation works as smoothly as I hope it will. The last speech I gave was at my wedding, so hopefully this will exceed that day as well. What I'm here to talk about today is Severn Trent's journey towards a nature-based approach over the past 6 to 7 years. I'm Matt Palmer. I'm a process engineer from Severn Trent. I also work alongside our innovations team and our capital teams to try and develop nature-based technologies for wastewater treatment. My colleagues Ryan Smith, Richard Smith, Andrew Richards and Alex Cook also contributed to this presentation as well. I'd like to start by defining how I'm going to talk about nature-based solutions in this presentation. So while specifically I'm going to talk about wastewater treatment applications, they are ubiquitous across the kind of water cycle and can be used for a number of other different applications. So by nature-based, I'm going to include everything from grey-green, which we possibly call biomimicry, so taking natural processes into industrialized processes, all the way up to kind of green-blue, which would be kind of constructing artificially natural habitats, so the kind of large-scale wetlands and or ponds, and everything in between. And the best way I think of it is to think of it as working with nature. So how do we benefit from the kind of natural processes that dictate a lot of the kind of natural wastewater treatment that we would normally see? And where possible, how can we use that to benefit ourselves in an ecosystem services perspective? So the journey towards a nature-based approach at Severn Trent starts in the kind of AMP5 period, roughly 2014. We have a lot of small sewage treatment works, anything below 2,000 population equivalent. Roughly 60% of the 1,000 sewage treatment works would be classed as small, and the majority of those are in areas that we would class as rural or difficult to get to. So typically these small works are fairly easy to run, but they are quite they're quite high in their kind of capital costs and their operating costs per person served, given their kind of decentralized location and given the kind of challenges in reaching some of these sites. So the rural strategy was developed by experts at Severn Trent, and I very much stand on the shoulders of those giants, and kind of consists of 3 main ideas. So first main idea would be a move towards more passive operation. At the time, this was focused on reducing carbon emissions via electricity use and to try and reduce the kind of operational spend of electricity. Now that kind of it also plays into the fact of us trying to reach net zero. So how can we, if possible, reduce carbon sinks? The other aspect was trying to reduce the local impact of these smaller rural sewage treatment works. So typically a large tanker removing sludge from a more rural agricultural area is quite a significant nuisance and can cause quite a lot of disturbance to our customers. So is there a way that we can make our sewage treatment works less impactful on that local customer network, and if possible, actually benefit them? And then finally, a focus on enhancing the local environment. So where possible, can we provide assets that not just clean the wastewater and benefit the river quality, but can we provide assets that really do give back in terms of their ecosystem services, so temperature reduction, biodiversity, etc. That was the rural strategy back in AMP5 in 2014. So since the early 2000s, late 1990s, Severn Trent have used combined and tertiary horizontal subsurface flow constructed wetlands, or reed beds, for a number of tertiary and combined flows operations as in sewage treatment works. There's quite a large asset base of those assets, and we are very proud of how they run as a passive way of dealing with those treatment issues. Towards the back end of AMP5, we started using those assets as aeration for removing additional ammonia, and that's something that's continued and is now embedded into our technological portfolio. AMP5 and AMP6 approach the rural strategy as an innovation technology, so we found new technologies within our context and trialled them. So one of those was a facultative lagoon at least resonant, an entirely passive descriptive type process where the aim is to reduce the kind of sludge tankering and run everything offline without connection to local electricity. And we've also talked before about Hull and Ward, which is a two-stage vertical flow rebed design, again aiming at that largely passive technology and looking to reduce the sludge tankering movements. And in AMP6, we also extended our rebed designs to include vertical flow to increase the application potentials of those reed beds. What I would like to focus on today is the past 3 years. The phosphorus challenge that our industry faces means that we have to try and find better ways or different ways or more ways of addressing phosphorus at small rural works. So we've expanded the kind of rural strategy to include nature-based solutions. Some of those items you can see on screen. We've had a knowledge exchange on wetlands with Irish Water, looked into algae, investigated reactive media, and looked into catchment nutrient balancing over the past 3-year period, including during the pandemic. And all of that work has led us to a nature-based toolkit. The nature-based toolkit is intended to be a series of technologies that we can choose at the right application of it. I'm not going to claim that every small sewage treatment work should be run as a nature-based technology. It might not be appropriate for every type of treatment that we have, but where possible, we want to try and make sure that we have a wide enough range of technologies available to us and approaches that means we can apply the nature-based principles to that. So on the left, we have the technologies that we're currently investigating or approaches for phosphorus removal. And on the right, we have our kind of more full sewage treatment works approaches as well. The parts of the toolkit in green are technologies that we have demonstrator sites for or a robust kind of asset base that we can rely on. The rest we're currently investigating in AMP7, and I shall go into more detail now. My colleague's presentation after me will discuss more about the algae reactors. So on this part of our journey towards a nature-based approach, what have we seen in the past 3 years? We've run in-house investigations into catchment nutrient balancing and have been working with the EA to put together catchment nutrient balancing potential proposals. Similarly, with algal reactor biotechnology, we've been working with the supplier and developing our own in-house feasibility for that technology. Free water surface wetlands or integrated constructed wetlands, we ran the aforementioned R&D and knowledge exchange with Irish Water, and we've also been involved in a feasibility study with the Rivers Ecosystem Services, and we've also been part of a larger industry effort to get this technology developed at the EA. And finally, reactive media, we've been looking at characterising different types of reactive media with Cranfield, market testing for potential different media from different industries, and running in-house kind of testing on the ability of those reactive media. So a little bit more detail on each of those parts of the toolkit aside from algae. So catchment nutrient balancing is an approach that looks to apply passive methods that work with the agricultural community to try and remove pollutants of concern from our rivers. So typically it's used in a drinking water protection angle, and Severn Trent have been leaders in that type of approach over the past 10 years. This work as an industry now looks to see if we can apply that logic to phosphorus. So what we've done is to apply a kind of tailored approach to this catchment nutrient balancing. We've built on the existing experience within Severn Trent's agricultural advisory community and the catchment management team. Ran detailed investigations with Stantec about each of the sites on the right to see if there is enough phosphorus to balance. We've also seen that the benefits of translating catchment work into a kind of capital side and the links between those two, and seeing how to translate catchment management or nutrient balancing potential outcomes into the impacts on the more traditional solutions, a kind of hybridized approach, as it were. And any catchment nutrient balancing work that we may do in the future would be part of a kind of national EA trial. So we've been contributing to discussions about how best for, as an industry, for us to do this as fairly and as reasonably to achieve the kind of same overall outcome. Our free water surface wetland, or ICW work, the key for us was to develop our technical knowledge base. There's a lot of ICW evidence already out there. What we needed to do was to see how to develop that knowledge base. So we've worked with experts and contributed to industry-wide research on potential phosphorus removal performance. And we've also critically tried to adopt lessons learned from SUDS design and or other type of wetlands installations to see how's the best way of producing these type of habitats while still focusing on the wastewater treatment part of it. We've ran feasibility for 6 sites with our consultant. We are currently in discussions about a trial site for one, though we haven't fully committed to that trial site yet. And in terms of supporting the wider stakeholder network, we've been an active member of the Task and Finish group looking at permitting implications and issues such as groundwater risk assessment. So reactive media, as I've mentioned before, probably the key progress that we've made is being able to in-house test our Severn Trent testbed. So this allows us to try and assess the potential impacts on final effluent pH and potential phosphorus removal ability of the reactive media. And this builds on work that's been done previously at the Packington trials that looked at steel slag and other work in the industry. We've also been working with suppliers, liaising and discussing with the water companies and contributing to the industry-wide steering group on reactive media to try and share our knowledge from what we find and kind of develop a consistent approach. We're currently trying to work through technical solutions for reactive media refurbishment and for flow distribution onto those reactive beds. And that brings me on to some of the challenges that we've learned and some of the challenges that we try to overcome with trying to work towards a nature-based approach. The first, speaking as a process engineer, is that as a natural process, we can't necessarily turn up or turn down the performance of a nature-based solution as easily as we could, say, for a more intensive type technology. Whilst that's clearly a benefit in some respects, it does mean that for the really tight P permits or the really tight ammonia limits, a nature-based solution is going to have some limitations. And given the kind of longer term trends of some of these type of technologies, some of that uncertainty is always going to remain. So where possible, we've tried to address that by trying to find the right research or trying to ask the right questions but otherwise it's going to be a case of working and trying to run those trials as best as we can. A nature-based approach is quite different to how we currently work. So another challenge is to develop the kind of operational knowledge to assess what might go wrong or what needs to be addressed. On the face of it, some of these things seem fairly simple, but how we respond to those in real time, or if there was a kind of performance issue on site, analysing those might be more tricky. The other major barrier to implementation that we've seen on our current journey is the kind of typical footprint or program of a nature-based approach compared to a more conventional. So typically these technologies do require quite a large area to fully properly work and address those performance uncertainties. And that can have an implication on the ability to deliver a nature-based solution for a specific scheme and the impacts on program through the kind of necessary actions to do some of that. So within a kind of AMP, the number that we could try to look at was restricted by land availability, for example. And I think finally, and this is more of a longer term challenge, how do we fairly quantify and include the benefits that these nature-based solutions provide? I'm thinking slightly outside of the kind of carbon angle or the traditional 6 capitals. Whilst we know that there are great biodiversity benefits, how do we make sure that we're fairly and accurately comparing the positives from a natural capital approach against some of the other more potentially capital intensive reasons for a nature-based approach? Challenges I think we can overcome, but challenges that we're still trying to work through. So I'm going to end the presentation with, I think, a couple of slides about the main lessons that we've learned. And the first of these is going forward to reach a nature-based approach, we have to be prepared to embed those nature-based solutions into the more traditional optioneering approach. It's always tempting for me personally to try and protect nature-based solutions and to treat them independently. But what I've certainly seen is that actually it's best to include all of the options together in one and to appraise them as fairly as possible. So given that some of a site may have a number of potential opportunities or options, we need to develop the way of appraising which approach is most suitable for a given site to focus on that approach. We also need to be able to retain the ability to investigate new technologies as and when they develop to allow us to expand that nature-based toolkit. I think the other key thing with that appraisal section is to develop fair and robust methods that can compare each of those technologies together as reasonably. That allows us to assess where it's best to focus on the nature-based solutions and where it's perhaps offset by other things. From learning in the technical solution, there really is benefit to treating nature-based solutions as we would with a hard engineering solution, to take seriously the kind of civils elements of it and the hydraulics and the landscape layout. That way it both eases the kind of integration of a nature-based solution into this optioneering or traditional feasibility approach, but it also means that we can kind of answer questions more upfront about how that will look. To borrow a quote, wetlands are more like architecture. So it's about trying to translate what that means into the kind of traditional engineering and how it will be delivered. And I think finally, we do have to accept that there are things we don't necessarily know, and we have to develop plans to address those knowledge gaps through the kind of proposals that we put forward, and understanding where each potential nature-based solution poses a unique challenge that we've maybe not had to address before. And finally, engagement of stakeholders early is a really beneficial idea, because it allows the kind of those challenges or those knowledge gaps to be addressed much earlier and to address those issues as and when we can. My final slide expands the nature-based approach from where we've currently looked at it. So my work and my colleagues' work has focused on wastewater treatment and pea removal over the past 3 years and past 6 years. What we've realised, though, is that a lot of the challenges that I've just discussed and a lot of the approaches that I've just discussed do apply to all sorts of other areas within the kind of water cycle. And the previous sessions on circular economy have hinted at a similar idea. So my question going forward in the work for myself and to the rest of the industry is, how can we take a nature-based toolkit approach and expand it so that we include all of the water cycle, address the challenges that we face as an industry holistically? For example, there's a lot of links between the catchment management side and the wastewater treatment side, and management of stormwaters and infiltration affects wastewater as well as CSO. So I see this as all being linked, and I see that a kind of centralized nature-based toolkit approach where we can share the lessons learned as a really key aspect of the future of a nature-based approach. I'd like to finish by thanking a few of our colleagues who aren't listed as authors, and I will add Pete Vale as one, because I think he's in the room. But yeah, thank you to Joe Souza, Jack Harris, who's previously done work with this, Joe Follows, Sarah Mitchell, Chad and Carl, because a nature-based approach comes from just more than just one person. It's about embedding that within the kind of engineering core, as it were. So thank you again. Thank you for listening, and I welcome any questions or any further discussions elsewhere.
So thank you, Matt. So time for a question, if anyone wants one. Yeah, back there. Francis, behind you.
Thanks, Francis. Hi, Matthew. Thank you very much. That was a really interesting overview of the Severn Trent NBS approaches. My question was about, I guess, the evidence base, both from the literature and also the mechanistic, like what we know happens in integrated constructed or free water surface wetlands or treatment marshes in terms of phosphorus removal. I just wonder what your thoughts are there in terms of what we do see or what we should see or what we could hope for in terms of P removal.
Yeah, it's a really great question. I think there's a session on ICWs later as well, so I'll probably only offer my kind of personal view. From what I've seen in the literature, I think phosphorus removal is achievable. I think we have to recognise that the mechanism is around phosphorus capture and cycling. So in terms of robust design approaches, it's something that I think as an industry we are trying to work through as a kind of realistic target. As a natural-based process, it has the ability potentially to be far better than a kind of more chemically based phosphorus removal, but I think there is also the potential for it to be more variable.
Okay, thank you. If it's quick, you can have a question. We're getting back onto time so that we can have our lunch.
Really quick one, Matt. Thanks for that. It just struck me that one of the issues you're dealing with is lack of intensity. But I was just thinking that Microvia were doing a parallel presentation at the moment. There's a possibility perhaps of combining technologies, so you could introduce carriers with biomass, specifically selected biomass, to add some intensity where it's lacking.
Yeah, I think that's a really good point. I think perhaps something I should reiterate is that I think a hybridized approach of nature-based solutions and other more conventional technologies or intensified ones is absolutely a way forward. There's work from Jacobs, I think, in the US about kind of supersaturated aerated wetlands, for example. And there's kind of various other technologies on the kind of market that kind of apply those kind of more intensified processes and focus on that nature base. But yeah, I can't see why we couldn't have a mostly natural flow sheet and then a kind of intensified process at the back end for those more specific pollutants.
Okay, thank you, Matt. We're going to stop there and we'll move on to the next presentation, which is again from Severn Trent, Carl Kissack and Shahad Al-Janabi. I think, are they online or are they live? Oh, you're real. Okay.
Hi everyone, my name is Shahad. I'm a senior design engineer in Severn Trent, and my work is mainly focused on wastewater treatment works, and as well as I've been involved in driving the AMP7 resilience trials, as well as I look at some capital maintenance and quality schemes. Today we will be sharing our journey looking at the algae bioreactor for phosphorus removal and ammonia. And this new initiative of the work is really part of our company to be more sustainable and try to build resilience, to reduce our reliance on chemicals, both as we know from an OpEx and an availability point of view. And the work that we have been doing so far is looking at how we can reduce the risks and the costs to allow us to apply the technology on a full scale and make it more cost competitive with the conventional options that's available now in the market for pea removal. So I'll leave the stage to Carl to take us through the AMP7 challenges and we'll look at it.
Thank you. Thanks. I'm Carl Kisak, Senior Process Engineer for Severn Trent Water, so I've been overseeing the algae schemes from a process perspective. And firstly, I'll take a step back. It's been mentioned a few times today, the size of the challenge in AMP7. So briefly, this is the Severn Trent quality program, so 166 works upgrades, 400 million capex, phosphorus limits down to 0.2 milligrams a litre. Alongside that, we have our internal capex challenge about trying to find efficiencies and do things more cheaply, and the chemical use increasing, and then the associated carbon footprint with that and building the technologies. So just in the bottom left, there was a forecast from a while back of us saying in AMP7, what do we think our chemical usage is going to be? And the forecast was for it to double over the AMP, and I'm sure that's pretty consistent across the other water companies as well. Right, so more specifically, within that program, there's a subset of really small sites, 61 in particular. As Matt mentioned, below 2,000 PE is what we refer to as our small works. They also have a range of different phosphorus limits, so that presents a broadly new set of challenges to water companies of what to do. You don't want to really be installing chemical dosing for 91 people or a phosphorus limit of 4.6 when your inlet is probably not that much more than that. And alongside that, as Matt's mentioned about our nature-based solutions toolkit, we wanted a specific focus on these sites to say, well, can we do something different than what we could easily do? We can install chemical dosing and TSR and meet the limits, but that's not what this is about. So we looked at these 61 sites, as you'll see on the left of the waterfall, narrowed them down a bit, because again, like Matt mentioned, they're not all suitable for these kind of technologies, and then had this forecast to say what might be possible for us to do in this AMP in terms of deployment of these technologies. So particularly, obviously, we're going to be talking about the algae segment of that, where we were targeting a few sites for the AMP. So what is special about algae? On the left there, just briefly, this is what they kind of look like. I'm sure you're all vaguely familiar. I'm no expert in phycology, but I know they come in lots of different shapes and sizes. They're pretty much everywhere, all throughout the world. There's some freshwater algae, but the key thing is they are photosynthetic, and they have chlorophyll, which is like the engine of the algae cell. On the right, I mean, it reads like a dream list of what you would want for a small works in terms of phosphorus removal. The phosphorus, I believe, is 0.1 kilograms per kilogram of algae, which is about double what we'd usually get out of a bio-pea plant. So in terms of phosphorus removal, it's actually quite an intensive process. So generally speaking, if you're familiar with algal treatment technologies, you've probably seen this bit on the left where you're saying, I just need a food source, the algae, which needs the CO2 to grow, and then light, and that's going to be your treatment. That's how your phosphorus is going to be removed. So we can provide all of those things in our sewage treatment plant. It's worth saying that this would also be a process that would be a tertiary treatment stage, rather than a secondary treatment stage. So it's all about polishing at this point. Then the next step is that we need to harvest the algae, because we don't want to just remove the phosphorus and then discharge the algae into the river. The whole idea is keep the algae away from the river. So you then need to separate the algae out, and then you have your final clean effluent. Severn Trent have some history in this arena. So this picture shows the Packington trial plant, where we were using encapsulated algae, which is shown on the right. So the algae was held, immobilized, so you don't actually need to separate it from the final effluent. It's already pre-separated in a sense, and it can remove the phosphorus by passing through the surface of the encapsulated bead. And what we've shown at this trial from AMP6 was that, yes, it will remove phosphorus, but it's quite difficult to make this encapsulated algae and to make it like in a mass-produced manner that makes it really possible to make in that kind of number and then keep supplementing the new algae and so on as the plant lives through its life. So finally, there's been some new innovations in this world of algae, and particularly the IFIC process that we've been looking at has introduced this new step that I think they would call it the conditioning step as well. And it's, in my mind, a little bit akin to EBPR. So you have your normal process, but now you're adding some additional steps that really supercharge the pea removal process. And really, it starts with the separation of the algae through a centrifuge, which means you've got your clean effluent, which has a lot of the solids removed, but also your algae is then quite thick. And then it's a lot easier to go through some processing stages, and you can keep it for a longer amount of time than if it was really thin. So we have the thickened algae, it's retained, it's kind of, I say mistreated, it's mixed, it's starved, it's lit, it's put in the dark, and then it's brought back into the process at the controlled points. And the main reason for doing that is you then get the really hungry algae right near the end of the process, so you can reduce the phosphorus really low. Whereas more conventional algae removal processes wouldn't go as low in terms of final effluent phosphorus. So now we've established the technology and how it generally works, we had to think about how we would apply it in terms of our process designs, at least internally for Severn Trent. So there's some characteristics that are quite important for us to at least start making our inquiries with the suppliers. So we need to know how much phosphorus is removed, what phosphorus level will come out of the system, because then that narrows down which sites we can look at. But also, on the flip side, is how much flow needs to go to the algae treatment process, because if we have a more relaxed phosphorus limit, we can actually reduce the proportion of the flow going to the algae process. And that's what this graph shows in the bottom left. Our assumption about the algae effluent is about 0.4 milligrams a litre. The red line shows the influent or the bypass, and then the green is the blended versus our dashed line, which is the permitted limit that we're designing to. So in this case, we're passing about 80 meters cubed through the algae unit, and then after that, all flows are blended, and still we're keeping the phosphorus below the target limit. So we don't have to treat all flows up to 500 meters cubed plus per day, which would make the unit much bigger. There's also a few bonuses that come along with that. The main approach was to look at phosphorus, but also it could help ammonia compliance because it's going to remove ammonia too. The centrifuge could help on solids compliance or BOD compliance if there's some issues there, particularly at poorly performing biofilter or RBC works, you might have some issues there. And alongside that, you have some risks that we were considering when we first looked at the technology. What would high solids do? Because you do get sloughs and things like that. Would it block the lighting? Would it take over from the algae? Could low or high ammonia threaten the pea removal? Because maybe it will preferentially remove the ammonia rather than phosphorus. Would the pea performance be variable or temperature dependent, as all biological processes are? And then we were considering, will we be able to fit this plant on the site? Because we've got a lot of small sites which sometimes don't have that much room available. So now I'll pass back to Shahad to talk more about the selection process.
So out of the 61 sites that we have had the small works, we had to put some sort of a selection criteria for us to decide what sites we need to do and focus our work on. And our selection criteria really focused on removing the sites that had a relaxed P permit. It was only one site out of those 61 sites which had a P permit of 4 milligram per liter. That was for us too relaxed. We also removed sites that already had a P limit on them, so they were already dosing chemical on site. That wasn't possible for us. We removed sites that had a catchment area of more than 1,000 PE, and the reason for that is we want to focus on small rural sites because of the challenges that we face from chemical delivery perspectives, as well as tankering and sludge, as well as reducing the cost of the package plant itself and make it more compatible with the having a chem dosing on site. And also, for our program, we had to remove the sites that had already a single solution in place, and the gate 2 date for them was last year in July. And the reason for that is we tried to build a kind of a contingency in our program and a plan B. If this technology does not work for any reason, we still have time to go back and put some chem dosing on site, because all these sites that we picked up are real sites and we have to meet the permit by the end of this AMP. Our selection came down to 3 sites. The 3 sites, the population of them ranged between Yackleton. Yackleton was a small site, the P was about 200. It's an all flows work. There was no ammonia limit, and the P consent was 2 milligram per liter. On the other hand, we had Market Overton. It was a 500 PE catchment with an ammonia of 15 milligram per liter. The P was 1 milligram. And then we have Croston Corral was on the other scale, which was at 800 PE. And then again, no ammonia limit to that site, but we had a P consent of 1 milligram per liter. Both of Yackleton and Croston had capital maintenance drivers, as well as the quality drive that we had to meet. What we did is we kind of looked at those 3 sites and compared the algae option plus the capital maintenance drive versus what we had the notional solution of having a chem dosing and a TSR on site. So just to have a very quick background on each one of these sites, Croston Corral, if you can see the process on, these are kind of the further layouts and developments of the site during optioneering and outline design. With Croston Corral, it's a very small, simple site. We have an inlet at the beginning of the works. All the flows go through 2 PSTs, dormant tanks, and then from there the flow will go into, let me try to use this, yeah. So we have a single biofilter, and then from the biofilter all the flows goes to humus tank. The algae bioreactor on site is basically designed as a TSR, so it's going to be at the back end of the works, and the aim was we were going to be treating part of the flow, and then we will be blending the overflow from the works at the back ends of the work. The things that during investigation we further looked at is what is the influent P to the works. So for Croston Corral, it was quite weak, between 2 to 4 milligram per liter influent P coming to the works. We designed the algae package to treat about double the dry weather flow. So we were looking at 394 cubic meter a day, plus the capital maintenance drive on site. So we were looking at introducing desludging for the PSTs and the humus tank, as well as adding a new sludge holding tank and doing some configuration work to the final effluent chamber. The other hand, Yackleton, it's a very small rural site. It's a single RBC site, so all the flows come by gravity to the works and then pumped to the RBC, and from the RBC to the final effluent. The interesting thing about Yackleton was the incoming effluent ranged between 7 to 11 milligrams a liter, and the algae was designed to treat about 81 cubic meter a day flow. If you can look at the operational boundaries of the site was quite tight, so we had a challenge of how we can fit the algae bioreactor on site. And although we own this kind of part of the land over here, however, that land was used by one of the neighbors, and Severn Trent, they decided somehow to use it as a garden. So one of the challenges that we had is how we can claim that land back from our neighbors without, kind of impacting the relationship between a client and a customer, and how would that impact on the back end of the program? So as you can see, that was one of the main things that, we were considering for Yakulton, as well as the capital maintenance drivers for Yakulton. We had to upgrade the pumps that's feeding into the RBC, doing some work at the final effluent chamber, and adding an extra storm storage capacity on site. So part of our AMP7 new work now at Severn Trent, we do outline design in-house, and with outline design, we have to conduct swift buildability, operability reviews, and all these have to go alongside with the operators to get the operators buying in to any new process that we introduce to the site, as well as we have to make sure that the technology comply with our own standards. And we have what we call in Severn Trent our standard deviation board that we have to go to and make sure that we reduce the level of risk, as well as we get the business buying in to the technology. And as because we mentioned that the algae is classed as a tertiary treatment to the works, so the closest things to our standards was our TSR kind of design manual standards. And for the algae package plant, when we kind of looked deep into it during our reviews, the single point of failure for us was the centrifuge, because if we lose the centrifuge in that package plant, that means the plant will shut down, and it's that the centrifuge is where the process is we extract the algae from the final effluent, and then we blend at the back end of the work. So looking at our standards for a TSR installation, if we treat more than 2,000 PE, that means we need more than 1 unit to be provided in place. And in our case, is because all our sites are less than 1,000 PE, so what we have to do, if we're providing a single unit on site, we need to make sure that we do have additional features in place, and the site must be compliant and still be compliant while we are kind of planning any maintenance or any operations to site. Sorry, 2 minutes. Sorry, did they take up time? Yes, I think so. Sorry. As well as that because of the nature of the single unit, we need to make sure that that we do any sort of balancing ahead of the works. As like tankering or anything, we need to make sure that we do provide these facilities. So for Crost & Carrell, from the supplier itself, they already have decided that we do have 2 centrifuges for the design. For Yakulton, there was only 1 centrifuge provided, and that's why we had to put a plan B in place. We do some tankering or some sort level of agreement of a maintenance to the centrifuge if we want to go ahead with that process. I'll try and speed up. These are the main things that we picked up from our ALM and buildability reviews, and they were mainly focused on the lighting, how we can protect the algae system, how we can control the system with all the other M&E control panels and kiosks, because they're all proprietary, how we make sure they all comply with our Severn Trent standards. I'll leave this quickly to Carl.
Thank you.
This one.
Yeah, very quickly then.
Very
yes.
quickly.
I mean, a lot of these considerations, you can refer to them because maybe if you're considering algae yourself, you might think about them as well, or before they come up. But also, just briefly then, optical density is a measurement that's used to measure how much algae is in the system, which is new to the water utilities, I believe. So we'd be looking to provide that and see if we can do some on-site testing for our operators. Again, we'll try to minimize the number of visits, but it's all going to be dependent on how stable the process is. In performance testing, we've planned to have something that forms part of our contract that's longer than normal. Normally it'd be 4 weeks, but we've got 6 months worth of sampling to check performance over different periods of weather and so on. And then we've got a longer term sampling plan to assess performance. Okay. So very briefly, originally normally we would set our performance targets based on the blended final effluent, and that's what we'd give to our contractor, but with algae we've set it before the blend, so purely we're getting our guarantee on the algae effluent to try to simplify things for our contractor and their risk reviews. And just back to Shahad to wrap up.
And I think it's kind of the final stage was for us is after we finished all the CapEx calculations, the REOC, we had to feed into what we call a 7 Trend TVT tool, total value tool, and that tool includes the carbon impact, includes the customer impact, so it's kind of a qualitative and a quantitative assessment to any solution that we provide. We had to go back to the business to share our findings, and then we ended up with 4 options. Either we proceed with algae solution on both sides, but that means we're way above budget, and the reason for that is during outline design, we had to put more design into the algae plant to make it more resilience and use it on a long-term implementation, not as a trial plant. We produced with algae solutions, however, we open up to wider competition because, as I said, we were lucky enough to get engaged with IFIC and a contractor early stage on board to learn from the lessons learned from Broad Windsor. However, that meant we would lose the plan B, the time in the program, and that was too risky for us. Option 3 was the favorable option, is that we deliver Crowston Carrel, but we drop Yackleton. We will be still within budget. However, the challenges with Yackleton, with the neighbor, and we need to cut some more trees, and that would impact on our biodiversity driver for the business, which means it's going to be a very challenging and long-term impact. So, or we revert back to conventional solutions, which mean we lose the opportunity. And I think we were lucky enough that we got the business support, and the business was keen for us to move forward with our kind of initiative in looking at algae. And finally, what I just want to say is applying this technology, I think early time in the program for us would allow us to understand more about the benefits of this technology on a full scale, as well as with all the monitoring that we put in place. Hopefully it will open more opportunities to roll it out maybe in AMP8, and if we can achieve some more optimization to the technology itself, we can do some cost reduction and apply it on a larger scale, as well as if it overperforms, that means it can open doors to more removal of microorganisms, pharmaceutical, hazardous substances. This is not only, I think, for today. We're looking for the future. We're looking to implement it in our PR24, hopefully, program. And finally, I just want to say thank you so much to Wastewater. I don't know if they're in the room or not, but Ruth, they had the Broad Windsor plant. She was so collaborative, so open to share with us all their lessons learned. And we have Narinda in the back end of the room. He's doing the technical team, looking at the algae treatment plant and how we can make it more, I think, suitable to kind of meet our drive in being more sustainable and less reliance on chemical. Thank you very much. Thanks a lot.
Well, thank you there. You speeded up very well. Okay, so we will get a few questions because it's not fair not to have questions. You'll just have to be hungry.
Everyone's hungry.
Thanks, Martin. Hi, really interesting. Thanks for sharing that with us. I have a question. With all these process engineering and highly qualified technical people looking at this technology, because of the complexity of it, how do you think their handover and the long-term operation of these plants is going to run?
Well, yeah, it's a good question because obviously we've considered it quite a lot, but as far as we understand, the control system should be set up such that it should be quite resilient for us just to check in on it occasionally in line with our conventional kind of monitoring of a few days per week, 3 times per week, something like that. But at the end of the day, I don't think we know until we've seen it running full scale, hands off, and we're not quite there yet. So we believe it's possible, and we don't know what changes will be required to do that.
Okay. Yep. Gerald?
Thanks. Gerald Noon, retired. Congratulations, that's wonderful breadth of thinking. Really, these are just a few queries. You mentioned blending. So I was intrigued to see that the size was double the DWF. So are you putting in storage to recirculate, or have I got it completely wrong?
Yeah, so the plan for blending would be only to blend at higher flows. So baseline flows would go to the algae unit, all flows, and then...
So you've sized it for 2 DWF?
Yes, yeah, that's right.
Okay.
Yes. And then any flows above it will bypass.
The other thing concerns centrifuges, because perhaps I'm too old, but I wouldn't have thought, how big are they? They must be quite small.
Yeah, I believe they're kind of food grade centrifuges. The one we've seen at the Broad Windsor plant is fairly small. I'm looking over to Thea, but because she's talking later from IFIC, so she might be able to answer that. But it's small, yeah. It's not like sludge treatment centrifuge. It's
And
food
that got
grade.
me into the other worry that I've always had with centrifuges is the coagulant aid. If you need one, do you need a coagulant aid?
So there's no coagulant, no.
Okay.
No. Yeah,
fine.
that was quite key for us to be chemical free, yeah. It was one of our worries too.
Okay, we're running out of time. Oh, but I'll just ask my own question. What happens to the surplus algae? Where does that go?
Yeah, so at the moment the plan is just to go to conventional digestion, but it's another area of interest, I suppose, in whether that can be used elsewhere or direct to fertilizer, who knows? Because there's a lot of interest in that
I think
area.
that was one of the challenges we picked up through our reviews is the surplus algae. We need to make sure that can we blend it with our existing sludge and tanker it away, or will we use it on something else? Yeah. And then we think that that's one of our lessons that we're looking to pick up and learn.
So you'll find out when you get it, won't you?
Yes, exactly.
Okay.
But there's not loads of it, I suppose,
Yeah.
is the other point.
Thank you very much to the speakers. Lunchtime, we'll just give them a round of applause again. of the Natural Solutions part of the conference. We've got 2 speakers this afternoon. First speakers are Ross Turnbull and Amanda Ludlow from Stantec, and they're talking about algae. So can we have the presenters up, please? Obviously not. Oh, maybe online. I'll start again. I've already announced this one, but we don't seem to have anyone presenting. Does anyone know where the presenters are? Are they online?
Hello, Martin. Can you hear me?
Oh, hello. Yes. Hooray. Off you go. It's your go. You've got 20 minutes.
We're ready to present. Can you see our screen?
Yes. Off you go.
All right. Well, good afternoon, everyone. My name's Ross Turnbull. I'm a process engineer based in Leeds with Stantec. I work primarily as part of the strategic planning partnership with Yorkshire Water. And I'm here with my colleague, Amanda Ludlow. She's a principal engineer based over in Stantec, USA in Vermont. And she is an expert on integrated constructed wetlands. We are here today to present on Clifton STW, specifically the integrated constructed wetland that's been sized specifically for phosphorus removal. Wetlands are very much an established wastewater treatment technology for conventional municipal treatments, but this one's been sized specifically to meet phosphorus consents for AMP7 YNEP schemes. Before we start, I'd just like to make the following acknowledgements, specifically to Yorkshire Water, our client, Stephen Spall, Tom Taylor and Mike Crow, the project team at Stantec, particularly Catherine Green, who was project technical lead, and Robert McTaggart, our delivery partner, Bar Hill Doosan, who are currently constructing the wetlands, Penny Anderson Associates, particularly Pete Worrell, who helped us with the initial concept sizing of the wetland, Kier, who provided us with some investigation works at the beginning of the beginning of the project, and finally Ryan Hanley Engineers, particularly an engineer, Stephen McCulloch, who's been seconded into the Stantec team. In terms of the agenda then, so I will cover the project background, give an introduction to the site, the future P consent, and the optioneering process we went through. I'll then hand over to Amanda, and she's going to present on the integrated constructed wetland concept and sizing methodology, the selected wetland design, and then we're also going to share some time-lapse footage from Bar Hill Doosan covering the construction phase of the project. So to give a background of the site then, we're considering the treatment work at Clifton, which is a very small village southwest of Doncaster. It serves a future population equivalent of 180 people. It's purely a residential catchment. There's no trade or employment contributions there. So it's purely just for the small village. AMP7 brings us a future phosphorus consent of 4 milligrams a litre. And we've negotiated an operational techniques agreement with the Environment Agency to sanction us to use the innovation of land treatment to meet this P consent. To give an overview of the existing works, so as stated, it serves the village of Clifton. It's effectively a treat all flow works, so all storm contributions are received. There's no CSOs. It's fed by a gravity inlet into the sewage works here. I'll draw attention to the very small footprint of land occupied here, and then this large footprint of land beside it relative to the size of the works. In terms of the existing works, flow comes in to this inlet flow chamber. It's received by a quite generously sized horizontal flow primary settlement tank. Secondary treatment consists of a package plant RBC with integral primary and humus zones. And the final effluent passes through a final effluent sample chamber, and it's actually discharged to the grass plot where we plan to put the wetland. We feel it's a tailor-made site for the integrated constructed wetland concept, owing to the small population equivalent relative to the large footprint of land that's available on the site. There were some challenges, given that the discharge is currently into the grass plot where the wetland's going to sit. This topsoil was quite saturated. There's ecological considerations. The ecological report did highlight nesting birds, and as part of the phosphorus removal requirements, we are proposing to use a clay liner rather than a synthetic liner, and this had to be agreed with the Environment Agency to prove that there was not going to be any groundwater contamination. If I move on to the Yorkshire Water business risk then associated with this project, so based on the sampled final effluent quality, the regulatory samples, it's very clear that the works wouldn't meet the 4 milligram total P consent. Additionally, there are self-reporting consents coming in, specifically 40 BOD and 60 suspended solids, which definitely wouldn't be met by the current works. The RBC is very much asset life expired, it's mechanically failed, it needs replacement. There's also a storm overflow which needs to be closed. So the works will now become a treat all flows works. The grassed plot discharge will also be moved to a nearby watercourse. As mentioned previously, the P consent, we've been granted a flexible permitting approach with the Environment Agency to trial this, and we believe it's the first OTA agreement for integrated constructed wetlands that's been granted to Yorkshire Water. I just wanted to give an overview of the conventional solutions. So a 4 milligram P consent would lead us down a single stage ferret dosing solution. It does lend itself quite nicely given that there's already a fairly well functioning position. To give an overview of the optioneering process then, so effectively we came up with two options: the nature-based solution, the integrated constructed wetland for P removal, and also the potential to use ferret dosing to meet the P consent. It is worth noting that both could be used in tandem. If there are issues meeting the P consent, we could introduce ferret dosing to the site quite easily, but we're hoping that the wetland should be able to comfortably meet the P consent. I'm now going to pass over to Amanda, who's going to cover the integrated constructed wetland concept.
Thank you, Ross. So constructed wetlands or treatment wetlands, also known as engineered wetlands, they've been around for over 100 years. Wetlands have been used to treat wastewater for over 100 years. So they are engineered systems to achieve water quality improvements by maximizing and mimicking the physical, chemical, and biological processes that occur in natural wetlands. Now, integrated constructed wetlands are a little bit different. These recently came about 20 years ago in Ireland with a focus not just on water quality improvement, but on the landscape fit and the enhancements to biological diversity. So the ICW concept is really originated with a surface flow, free water surface wetland, where you have a combination of open water ponds and shallow marshes. The open water ponds provide physical removal treatment mechanisms through sedimentation, but they're also help promote even conveyance and distribution into the shallow marshes. The shallow marshes provide filtration and absorption and uptake of nutrients. And the unique part of integrated constructed wetlands that are different than other treatment wetlands is that the focus is really on using native soils. So native soils as your liner, as opposed to an impermeable geomembrane or geotextile based liner system. Next slide, please. So this is a overview of the site. And as Ross was saying, that the wastewater currently discharges to the grass plot. The site just about is upwards of 3,000 square meters in size. So it was a very restrictive site. The initial concept that was developed by Penny Anderson looked at maximizing kidney-shaped, natural formed wetlands within this area with the goal of providing secondary and tertiary wastewater treatment with an area of about 2,500 square meters with an HRT of about 10 days. And as noted here, the flow is relatively low at 45 cubic meters a day. Next slide, please. So as we were furthering the design, there are really multiple approaches to how you can develop your basis of design. Typically with treatment wetlands, we're looking at the forced water plug flow PKC model, which looks at applying a number of tanks in series approach to a specific treatment design. So it's based upon the type of treatment wetland that you're designing, but also based upon your constituent itself. So it's based upon your influent loading rate, hydraulic loading rate, your influent concentrations, as well as your effluent goals. However, a lot of the removal rate constants that are available in literature are relatively new. So it's looking at more of like under 10 years of performance data to develop those removal rate constants, as well as a lot of the systems were significantly larger than and had larger flows than what we're working with for Clifton. So instead of using the PKC model, we looked at loading charts which were based upon about 160 small scale sanitary treatment wetlands that were free water surface wetlands. So when you apply an effluent TP concentration of 4, you can click one time, Ross. Then you can look down and identify an influent TP loading rate. So that tells us really what area we need to size the wetland for to ensure that the effluent total phosphorus concentration will be below 4. So this is how we further develop the design, also using the PKC model as backup. And one of the things that's unique about phosphorus is that we know we're going to get really good phosphorus removal in the first 4 to 5 years because of the native clay that we have and that we're using for the liner. We're going to have really good adsorption to that liner. However, the question then, once those adsorption sites are full, how is the phosphorus removed? It's typically removed through sedimentation and burial and more biological processes within the wetland, but those K values have not yet been developed for that. So one of the unique things about Clifton is that we're going to be able to develop future design criteria based upon the performance of Clifton, both in the short term and in the long term. Next slide, please. So when we apply that loading criteria, we see that we need to really maximize every square centimeter of land to make it a treatment wetland on the site. So we expanded the area from 2,500 to about 3,000 square meters and increased the HRT from about 10 to 12 days. Next slide, please. So some of the design details. We're reusing the existing primary sedimentation tank. This is definitely a requirement for treatment wetlands. We need to remove those suspended solids. We're decommissioning the existing RBC, but we're adding a primary basin to provide additional sedimentation. So we're reaching a 24-hour HRT for that primary step. Then effluent is distributed between cells 2 and 3, which are our secondary treatment systems. They are running in parallel, so we can distribute that high organic secondary load across 2 systems. Then effluent from those 2 cells 2 and 3 then flow to series to cells 4 and then cell 5, which are the tertiary treatment systems. All the hydraulic controls are managed through stop logs. as well as rock cascades in between each cell. So within each cell, we have a combination of open water and shallow marshes. The open water extends across the whole width of the cell to provide even distribution of flow into the shallow marshes, as well as collect the water on the other side and even flow. So this will help minimize short circuiting and reducing our treatment capacity of the ICW. Shallow marshes provide the filtration and adsorption. Next slide, please. So one of the great things about the ICW is that we're really focusing on enhancing biodiversity. So within our secondary treatment cells, we're using more robust species that are typically used in treatment wetlands that are adapted to these higher strength, higher organic loads. But when we get to the tertiary treatment cells, this is where we can really add a significant amount of diversity. And Penny Anderson has developed this really diverse plant mix of a variety of flowering species, as well as rushes and sedges, and really provide a food source for native, for surrounding birds, waterfowl. So there's a really nice diversity. And one of the things that's going to be really interesting from this project is to see which plants end up dominating and really be able to select for next ICW designs of which work well in this environment. Next slide. So to summarize, from the nature-based solution standpoint, integrated constructed wetlands are designed for water quality improvement, which helps to run, that these systems run passively, that there's no pumping involved, that they're completely passive conveyance, which results in low operation and maintenance, less burden on the operation of the systems, no chemical additions. We're also increasing our biodiversity, which makes it a much more sustainable solution. But in the end, it's not just about the biodiversity for the wildlife. We also are providing a public amenity to the community. Next slide.
So it's been very well publicized recently in the national press. There's been several news articles, positive news articles surrounding the ICW concept, and our client Yorkshire Water are very keen to tweet about it, and it's very good publicity for them. I'll now just pass over to a time-lapse video showing the construction phase of the project.
So it's just showing the PowerPoint still, Ross.
Yeah, I'll just get that set up. Stop share.
There we go. Good. So this initial photo series shows the removal of about a top meter of organic soil that was saturated from the discharges from the treatment works. That material was then moved off to an adjacent plot of land where it's being revegetated with a variety of native species, wildflowers, native grasses to provide additional habitat. So now you can see the underlying clay, native clay, really nice quality, it's gonna be great for phosphorus removal, great impermeable liner. You can see the cell construction of the cells. Cell 2, cell 3, and as it works down, gradient. And there's a step between each cell. So is it all passive controls through stop logs? You can see stop log structures and the gravel lined channels where there's a pipe going down the middle of that first cell. That is essentially a bypass pipe so that we can operate the first two cells in parallel. We also have bypasses incorporated into all the cells just in case we need to take one cell offline, provide maintenance. We can bypass around that cell. That's it.
Any questions?
Thank you.
Okay, thank you, Ross. Yes, thank you, Ross and Amanda. I think Amanda's in America, is that right? Yeah.
Yes.
Okay, so great example of people around the world doing something in Yorkshire. It's quite near where I live, that, so it's great. Okay, questions? Ooh, don't think we've got any. Oh, we've got a question there.
I don't want to try again. Thank you, Amanda Lake from Jacobs. Thanks, that was a really inspiring presentation. Interesting, because as you say, most of the similar systems elsewhere in the world are much larger scale, and so there's some interesting risks of bringing that down to 180 population equivalent, but would love to see it work. How long do you think you might see the P removal for? What do you think might happen to the P?
So yeah, we know for the first 4 to 5 years, possibly 7, we're going to have really excellent P removal from the absorption. So if we apply those kinetics, those K values of a new system, we're oversized. We will likely get down a P consent well below the 4. So the thought is that as the system matures, we may see some of the P values that are from larger wetland systems that have been in operation for decades. And some of those K values are significantly lower. So even if we look at those K values, it's still sized to meet that consent. So instead of say 1 milligram per liter, we may be at 2 milligrams per liter. So we've definitely provided some conservative features. And if we are having concern, if there is some potential phosphorus release because we are maximizing absorption site, we're not getting the sedimentation and the burial and the consumption by the plants, we also have a contingency that if we need to add a measure of ferric dosing or some kind of adsorptive medium at the end, we can do that.
Yeah, thank you. A question from Andrew, I think. I might have missed something on the sizing for an effluent TP of 4 milligrams per litre. Does that assume a certain inlet phosphorus load? Or
yes.
Right.
Exactly. Yeah, it does. And so we're looking at concentrations of around 8 with a little bit, some primary removal. So ranging between 6 and 8 for influent concentrations.
That's what you've measured, or that's what's assumed in the design?
Then measured from spot sampling as well, and then also is adopted into the design assumptions.
Okay. Okay.
The influent theoretical loadings correlate very well with the sample data we've taken.
Okay, I say one last question and then we'll move on.
Hi, Mike Jordan from RHDHV. I was just wondering whether you could comment on the seasonal variation in the TP performance and the re-release when you get dye back.
Yes. So you typically see 2 peaks in the phosphorus, especially in these colder climate wetlands. You'll see a peak in the springtime as the plants grow and take up phosphorus. You'll actually see a decrease in the summertime when it's already maximized their growth. But then you'll also see another peak in the fall, right before the plants go into senescence, and they're providing storage of that phosphorus to winter over. So you'll see poor phosphorus in the summer, mostly in the winter, obviously, because there's no plant transpiration, the plants are dormant, but also you'll see the next lowest removal rate in the summer. So what we're applying is more an average for the year. Median
Okay.
for the year.
Yeah, thank you, Ross and Amanda, and we'll close it there. Okay.
Thank you very much, everyone.
Thank you. Appreciate it.
Okay, next presentation is by Thea of Industrial Phycology, and she's going to talk about algae. Thank you, Thea.
I'm going to test this because the mic's been on and off. It's good. there's no presentation. The presentation. So firstly, I'd like to thank Carl and Shahad. Earlier they presented, he's just walked in, he heard his name, I ushered him. They presented what I thought was a really lovely, balanced discussion around why they're selecting microalgae. Now I'm going to answer the question that's on everybody's lips. Yes, I have managed to fill my car. I got it at Tesco Express. But that's kind of a jokey intro to what actually is a really serious issue. We're having supply issues. It was just pointed out in that previous slide, in that previous talk. We've got poor connections with HGV drivers, we're having issues with COVID, and our supply of ferric salts are reducing. So BioP removal, there's a screen down there. BioP removal is going to become one of the most important technologies within the industry going forward. I think it's a really exciting time for us, actually. We've also got this opportunity of a circular economy, actually seeing our waste as a resource. We really need to start changing our mindsets. Microalgae has also been demonstrated, and we have done this in IFIC, that we can start to look at removing emerging contaminants. Now, I think it's important that we don't say that algae is this awesome thing that is doing every single thing under the sun. Sun, joke. But I think there's a number of processes that are happening in line, so we may actually have some photodegradation happening of the pharmaceuticals, as well as adsorption and absorption within the microalgal cell. Also, we've got this amazing opportunity for carbon reduction. You know, these are photosynthetic cells, so for every 1 kilogram of algal biomass, we're removing 1.83 kilograms of carbon dioxide. So yeah, there's never been a more poignant time to talk about the issues around ferric salt dosing. And actually, this conference has highlighted to me that there are some really awesome things that you can do with ferric salt dosing if you do the right steps and the right preparation and you really think through your process. But we've got a massive demand. Stantec highlighted that earlier. We're going to have a 30% shortfall in the chemicals. So we really need to diversify. Like our energy and our transport sector, we need to diversify our options. So we're not just dependent on one system. The price is going to be volatile, and I have a feeling it's only going to go up. And then you've also got this kind of adding iron into our water networks. Algae love iron. Actually, when we were thinking about how to solve global climate change, one scientist said, let's dump a load of iron in the water because you'll have a huge algal bloom and it will strip out all the carbon dioxide. So we don't really want to be adding iron into our water. And you actually have shown that it is achievable, so ignore that. But you do need your assets to be in good condition. And specifically, when we're looking at these small rural treatment works, we're going to these works that, you know, through no fault of your own, you have had to prioritize your bigger plants first. And the smaller rural treatment works have been neglected. And so we're now having to make very difficult decisions where you have plants that haven't been thought about for a very long period of time. So quite often when I talk about algae, I start where you may be starting. Algae doesn't work. You know, you have to have these massive surface areas. It needs it for the light penetration. So this is what you're probably used to. You think algae, you think raceway pond. And no. So IFIC have spent a really long time trying to redesign our concept of algae. This is a raceway pond in New Zealand, and it takes over 2 hectares. So if we're thinking about our small rural treatment works, we don't have that footprint. As Shahad pointed out, they had part of their land taken as a playground. So sometimes you think you have a footprint and you don't. This is also the other idea you may have of microalgae. Now, this is only 30 meters cubed of algae, and they're in these like really attractive, you know, lava lamp style tubular raceways, but it's incredibly expensive. So again, not so appealing. Quite often with microalgae as well, they're dependent on the metabolic uptake of phosphate. So they need relatively long treatment times of 2 to 8 days. That can be highly variable and unpredictable. You then have to, a lot of people that use algae, they say, hey, we grow algae and we happen to treat wastewater. So we have to flip that idea. We treat wastewater and we happen to use microalgae. So we're not dependent on having to produce these niche products. Often you have these raceway ponds that, again, you're adding this variability of light, seasonality, photo periods. So we needed to try and remove as much variability because there is enough variability within the water that we're trying to treat. So, IFIC, here we are. We were fully aware that you guys have a shortage of green solutions for small rural treatment work, specifically reaching the less than 0.5 target. So we redesigned algae to try and achieve this by using more standard chemical engineering principles to create a formulaic and consistent treatment method. We utilize the algal cell essentially as a biocatalyst. We're no longer saying, we're just going to have a load of algae, put some phosphate in and see what happens. So we want it to take up phosphate every time, and we can't afford for it not to work. We want to try and minimize the production of biomass as much as possible, and we want it to do the treatment within a reasonable time frame. So instead of days, we want it to happen in hours. We want to achieve these low phosphate levels that you guys are having challenging conversations around, and we want to be a real option that's on the table. So we have achieved total phosphate levels of less than, of 0.05 milligrams. And an important consideration is how much operator input do you need? You don't want a site that needs a PhD sitting round the clock, 24 hours, monitoring your algae. So we've also designed it to minimize operator cost. So how does it work? This was kind of suggested or demonstrated earlier in the Severn Trent presentation. So running through briefly, we take generally tertiary wastewater, but we have treated primary wastewater with the solids settled out. In general, we're treating levels, well, at Broadwinds, around 7.5 milligrams total phosphate. We add what is the unique selling factor of IFIC, the conditioned algae. We have our specifically designed reactors where we spent a lot of time ensuring that we have the right light, the right intensity, the right flow patterns. The algae take in carbon dioxide from the air, but they also take in carbon dioxide from the bacteria that's present. It releases oxygen because it's a photosynthetic process. And we get our polished effluent with a little bit of microalgal biomass. So let's compare this to previous algal solutions. So the pink line is a tubular fence bioreactor that Swansea University used to remove total phosphate. You can see that it took about 200 hours. They were growing that in the creme de la creme of biofences. They may not have been wanting or focusing on how much time it took to remove the phosphate. But you can see with the conditioned microalgae, when you put the phosphate in, it's an extremely linear drop. We get really high R-squared rates, so we can get very predictable removal of phosphate. So there we're removing just about 7 milligrams down to undetectable levels in 5.5 hours. So let's go back in time. We have a demonstration facility at Weston-super-Mare. Our original idea was to essentially take the high-rate algal pond and see if we could make it suitable for the UK. So originally, we had in tank 1, treat it, tank 2, fill it, tank 3, harvest it. We had a 15-meter cube buffer tank there and a centrifuge. Now, the more we worked with our clients, the more we understood the problems that you guys were facing, the more we realized, okay, we've got a great idea. We can make algae work in the UK, but we need to get it faster and more reliable. That's the inside of the tank. Again, beautiful. So then we retrofitted the conditioning reactor. So we added that blue container there, which contained 10 1 meter cubed. So this isn't the professional, polished look that you would get on site, but this is part of our development. So we took our conditioned biomass and we demonstrated it in 26 meters cubed. So every peak is the influent, because this is a batch system, it's not a continuous system. And this data is our online orthophosphate. So, I don't want to move away from the mic. Point. Every peak is influent. Then you can see the sharp decline where the algae was added. Then we went home because we didn't want to harvest the algae. Then we harvested the algae and we added the influent, and we did that until the pandemic came and we had to leave. So this is where we're getting where we're kind of higher above the 0.5. Our key target was 0.5, but then we were playing with how much biomass we were adding. So could I reduce the biomass load a little bit? Should I increase the biomass load? So then let's make ourselves a little bit more professional. You guys have very variable flows when you're at a small rural treatment works, so we can't depend on having a batch system. So this is essentially our process, but in a feed and bleed system. So the influent comes in here, it feed and bleed through each tank. We add our conditioned algae, they flow through with an increasing level of light. So because the algae is conditioned, it can start taking up the phosphate without light, and then we just give it a little pick-me-up towards the end. It flows through the system, it goes through a food-grade centrifuge. So one of those questions was, what is the centrifuge? It's actually a brewery centrifuge that is designed to run 24/7, and it works really well. It then goes into the conditioning process. So it's a closed loop for biomass and an open flow-through system for liquid water. And then we store the biomass there. So this is Broad Windsor. A number of you may have visited us there. If you have, thank you. If you haven't, please come. It's a 490 population works. We're currently commissioning the process. We have had some teething problems. The majority of those have been mechanical and electrical. The algae, however, is removing significant amounts of phosphate. So we have had loads of up to 10 milligrams total phosphate, and we're getting it down to 0.52 milligrams. So we're getting there, and I hope that I can release some data to you by early December. Now, the other really exciting thing about algae is it's not a one-trick pony. It does so many exciting things, and that's why I love it. So you can see that here we've got a little sample from, I always say it wrong, I say it Yockleton, but it's Yackleton, I believe. And you can see that we're not just removing the total phosphate or the reactive phosphate. The ammonium goes down to very low levels. We've got a nitrate reduction, and therefore a total nitrogen reduction. We do see a little bit of an increase in COD. That may be due to EPS production. We need to look into that a little bit more. Here we've got a Welsh water sample, and we see a similar thing, complete ammonium removal, reduction in total N, a reduction in nitrate. So algae are really cool. I keep saying this. They have something that's called metabolic plasticity. So they're constantly reviewing their environment. And if they have no ammonia, then they can transcribe nitrate reductase and take up nitrate. So they're really good at finding all the bits and pieces that they need in the environment. So one question that I commonly get asked is, if they remove ammonium, will they still take up the phosphate? Yes, because the phosphate is being removed via transporters, and the ammonium or nitrogen source is being removed via pathways. So it's two different systems happening in parallel. So this is, I scoured a lot of papers to try and get a number. And the more talks that I've been to, the more I realize there's a difficulty in putting a number to the nitrous oxide produced by the wastewater industry. But this is a recent number that I could find in a published area that demonstrates that wastewater treatment sector is responsible for around 4 to 5% of nitrous oxide of the total anthropomorphic emissions in the world. Okay, that may not be the case, and you can reduce that, and I don't want to upset people. That's based on this calculation. With microalgae, we're not just converting the nitrogen or converting it via denitrification. We're actually assimilating it, so there is no potential for nitrous oxide production. It then also is providing this lovely oxygenated environment for any bacteria that is within the system. So you're reducing the chances of your bacteria releasing nitrous oxide as well. Then you're adding, lots of lovely oxygen. And they can assimilate and use a variety of nitrogen sources. What's really cool is that you can then do that in one footprint, so you get good bang for your buck. And as I said before, you're then taking in the carbon dioxide from the atmosphere, so we have aeration that has multiple jobs. That's for mixing, for mass transfer, for keeping the cell in suspension and moving the cell into and out of the light. So we are stripping the carbon dioxide from the atmosphere, the atmospheric levels, and from the carbon dioxide produced by the bacteria. We've also got an excellent opportunity for a circular economy. So what do you do with the bacteria, with the microalgae? There's so much you can do. It's amazing, some of the conversations that we've had. So for example, there's a guy in America called Scott Fulbright. He has a company called Living Ink. They take microalgae and they can print packaging with it. So microalgal cells are perfect for printing directly in a jet ink printer. So therefore, you no longer have to use petroleum-based inks. We've also obviously got the biofertilizer. It's an amazing biofertilizer, as stated earlier. So slow release, doesn't have the mineral runoff, so you're kind of eliminating the problem at the source and in the water. Plants grown with microalgae biofertilizer actually have a higher nutrient density. And then if we're talking purely about carbon sequestration, so there's that complexity, isn't there, when we say, oh, we're removing all of this carbon and then I'm going to use this with it, so I'm not actually sequestering the carbon, I'm just transferring the carbon somewhere else. If we're talking purely about carbon sequestration, then we can put them into resins or foams and actually lock the carbon away. They make a really great filler for things like that. So, thank you very much. Any questions?
Okay, fabulous presentation. Thank you very much, Thea. So, questions? Ooh, we're all slow. Right. Well, I'll just say, right. Oh, we've got a question there. Right. Lovely.
Hi, thank you for your presentation. It was really good. I'm Rowan Luck, Severn Trent Water. I'm interested in the ammonia nitrification side of things now. Some of the figures you put up, they were relatively low ammonia in and out. How far do you think you can push it?
So we've had some really interesting samples, not purely from wastewater. So an example would be shrimp waste. I'm trying to pluck the numbers off the top of my head, but I think we were able to move 25 milligrams. So the upper limit for algae would be 100 milligrams. That's when they would start to have toxicity from it. So I would say we could probably push it up to around 35 milligrams, and it would be a good removal level.
Thank you.
Okay, question at the back there. Hang on.
Hi, Thea. It's Shahad. Quick question about seeding the algae. Mm-hmm. So where has that got with Broad Windsor? And
So we finished seeding Broad Windsor. That was part of our, technical issue, is that we went from having our facility at Weston-super-Mare to then having to seed the equivalent of about 400, enough algae to inoculate 400,000 litres of water, which kind of quickly escalated us into one of the biggest algal producers in Europe, which was quite a big jump. But we're there now, so we've got all the algae that we need, and that's why I'm hoping that we can be generating the data that we can then present at future conferences, hopefully by December. And now we have that facility, it's significantly easier for us to seed our next site. It was just that big step.
Okay, and just a question from me. What's in the pipeline? Anything else? And we saw Severn Trent earlier.
Yeah.
What else what are you thinking about?
So I think we are talking with most of you guys at some stage, and I hope that we can, as we kind of demonstrate ourselves, I feel like we've got a nice queue of people who are just waiting for something. So hopefully, we can really prove ourselves and demonstrate that we have made algae accessible. It's been talked about within the water industry for 50 years, but I feel like we've really unlocked the potential of microalgae. So we are just waiting to take your orders, really.
Okay, we've just got time for one question, Steve. It's got to be quick. Yep.
Have you ever tried operating on a continuous slow basis? Have you ever looked at running with membranes or considered trying to other methods of sedimenting down and returning?
So Broad Windsor is operating on a continuous feed and bleed flow. Yeah. So it flows through 5 tanks. So kind of it is essentially one massive tank that operates continuously. It's fully automated. We've designed it so that it is built on skids, so we can design it to wrap around all of those crazy shapes that you saw at rural treatment works. So yeah, it's kind of interesting. When we were operating in the lab or at larger works, the algae behaved much more differently to at small rural treatment works, which is why we chose the centrifuge. And also, we've put so much thought and consideration into how to lock this phosphate into an algal cell. We don't want to then release that phosphate into the environment. So we wanted to be sure, and if you read any papers about harvesting microalgae, which is what I did my PhD in, it's a bottleneck for a lot of industries. So we wanted to go for the known process. However, once we've started to work at Broad Windsor, we are seeing that this biomass settles much more readily because of that symbiotic relationship it has with the bacteria. So I'm thinking that we could go for a screen or filtration and not be so dependent on the centrifuge. But we just wanted to really establish ourselves, demonstrate what we can do, and then start to diversify kind of the built-in options, I guess.
Okay, we'll call it there. Thank you, Thea.
Okay, good afternoon. My name's Dean Heron from Aqua Enviro. I'll be chairing the final session of the afternoon on bathing waters. So we have 2 great presentations from Stantec. The first from Christy White. So if you could come up, please.
I don't think it points so well. Have you got a timer? Sorry? Have you got a timer? Maybe do halfway through, yeah. Okay. Hi, my name's Christy White. I'm a technical specialist at Stantec. I'll I've probably spent the last 10 to 12 years focusing on disinfection and bacteriological reduction. This talk's probably going back in time a bit to start with, because I think we worked on a UK work project about 10 years ago where we started looking at bacteriological reduction and low carbon approaches and things like that, and it culminated in some work for the Environment Agency on changing disinfection approaches and things like that. So I've tried to keep it quite high level to come over with the whole approach, but and not get too in depth in the disinfection side of things, but we'll kind of see how it goes. So it's a bit of a change to phosphorus, sorry. Okay. Oh, I can do it. I do it, don't I? No one else does it, right? Oh, worked again. So we're going to focus on microbiological reduction, how it's achieved in wastewater treatment processes. There's three main mechanisms, so we'll go through those. We'll focus on the last bullet point, the reduction through wastewater treatment plant, but there's two other important parts of it as well, obviously. And then why are we looking at it? You know, what are the benefits of looking at site-specific reduction? Why don't we just assume things? So that's pretty much what we're going to talk about. Why? Why are we doing these things? The first couple of slides are just saying the context, so we're not talking about phosphorus anymore. Sorry, I know that was the rest of the conference. But Harry and I are going to talk about disinfection, because that's what we like doing. Shellfish waters, the only thing we couldn't find a map of is the Ireland one, so sorry about that to any people from Ireland. But there's shellfish waters all around the UK, obviously, and elsewhere in the world, but for us, around the UK. They're protected areas designated for shellfish growth. They change because shellfish water goes to different places. Shellfish goes to different places, generally where the wastewater treatment plants are discharging. They're filter feeders, and they retain the pathogens. And so any E. coli or viruses or anything that's in there get bioaccumulated. They're classified based on E. coli in the shellfish flesh, and there's a whole ream of information on the CFAS website that I'm not going to go into, but for example, you've got, if you're a Class B status, then you've got 90% of the sample results have less than 4,600 E. coli per 100 grams. But that's no good for us as engineers and wastewater treatment people, because we deal with milligrams per litre or CFU per 100 mil or whatever. So we need to sort of understand how that's translated. There are a lot of, sometimes when there's outbreaks of shellfish-associated incidents, it's as a result of CSO discharges or wet weather discharges. So the whole of the sort of continuous discharge disinfection side of things also twins very much with wet weather discharges and CSOs and overflows and that kind of thing. And although we measure E. coli, as we'll talk in a minute, most of the shellfish-associated illnesses are virus-related, like Norwalk virus or norovirus. I don't know if anybody here has norovirus poisoning, but it's not very nice. My daughter got it. And one of the things that's driving us in what did drive the AMP6 changes and the AMP7 changes is there's new guidance issued from the EA and the PR19 driver guidance, which highlighted a move to the target of 5 CFU per 100 mil E. coli at the shellfish water boundary from 110. And that's, if you've got a direct discharge to a shellfish water, that's quite a tough call. So bathing waters, that's the other main driver. And the UK's got over 600 designated bathing water sites now under the revised Bathing Water Directive. Apparently there were only 23 in 1976, so we've obviously gone somewhere. A couple of years ago, 98% of bathing waters in England met the minimum standards, and only 1.7% of them were classified as poor. So we're doing pretty well in general, aren't we? And although most of the sites, obviously the majority of the sites around the UK are on the coast, in the last few years we've been talking about new designations in rivers. There's one in Yorkshire, I know it sounds like Severn Trent are talking about them. And I think with all these people going out and swimming in rivers and stuff, I guess it was going to happen, wasn't it? I'm sure Salford Quays will be one as well. And this is, I mean, everybody can look up the bathing water standards, but basically you can see that it's driven by E. coli and intestinal enterococci. Why? Why, when everything that makes us sick are viruses? Okay, E. coli and enterococci make you a bit sick, make you sick as well, don't they? But you have to have a bacteriological infection. I'm not a microbiologist, I probably need to talk to Thea more about that. But we measure E. coli and intestinal enterococci because they're easy to measure. Easy, you know, you take it to your microbiology lab, be it CREH in Leeds or Aquavira, or not Aquavira, ALS, that's right. It's easy, it's cheap, it's standard, you can do it, but it doesn't tell you anything about the viruses that are in there. The problem is that, as you can see, the list over there that I can't point at, there's loads of them, and they make you sick in lots of different ways. But all the methodologies to measure them are very difficult. You have to have huge volumes. How are you going to do that from a regulatory point of view? You know, taking 10 litres of sample all the time and maybe measuring one, because they're very difficult to measure. And usually they're viruses are in concentrations that you can't measure very easily, whereas all the regulations tend to be around E. coli and Tesla enterococci because they're easy to measure. They're in enough quantities that you can measure them simply, and they're cheap to do. So that's why the regulations are around that, but it doesn't necessarily mean that that's there. But that's why predominantly we talk about E. coli and Tesla enterococci, but we have to think about viruses as well. So, the Environment Agency has withdrawn its EPR 7.01, which was how to comply with your permit, and there was a whole section on disinfection in there, but they've only withdrawn it because they're rewriting it to put it online. But basically the two main drivers for reduction over biological treatment are either your shellfish water ones or your bathing water ones, and they look a bit like that. And ultimately what we're aiming for is an E. coli of 5 at the shellfish water boundary. And there's another number you have to remember. So crude sewage, if it's the only number that anyone ever remembers is crude sewage, we assume, and the basis of all the kind of regulation is based on that, although we can measure it and things are different, but 2 times 10 to the 7 is our starting point in the crude. As a rough order of magnitude average, 2 times 10 to the 7. So we're trying to get from 2 times 10 to the 7 for a shellfish water down to 5. That's a lot of logs. In bathing waters, it's slightly different. If you remember the table 2 slides back, it had the EU bathing water directives which, numbers, which are in 95 percentiles. You can translate that into GMEs because it's just easier. So for E. coli, we're aiming for 80, and for intestinal enterococci, we're aiming for 32 in the bathing water monitoring point. Again, we have to get there from 2 times 10 to the 7. How do we get there from 2 times 10 to the 7? In addition to that, in England and Wales, the Environment Agency says, as well as, so this is where the 6.6 and the 5.4 log reduction of E. coli comes from. That's what we're trying to do. We're trying to get 5.4 log reduction for bathing waters and 6.6 log reduction of E. coli, as well as other things, but that's the simple starting point. But also the Environment Agency says, we want you to get 4.4 log reduction of virus. And that's how do you do that? And how do you measure it, and what do you do? So we're basically going to be focusing on how we achieve those boxes. There's a very simple wastewater treatment plant in the middle. So we start with crude sewage, we have biological treatment. I know everybody in the conference was talking about, we aim for BOD, don't we? BOD reduction, COD reduction, all the urban wastewater treatment stuff is BOD, COD, ammonia, phosphorus. But actually, from a public health point of view, what a wastewater treatment plant is doing is reducing the bugs that make you sick. So, as well as all the other things that contaminate. And biological treatment is quite good at removing bugs, but different treatment processes are better or worse, and it's very reliant on the operational conditions and the design and what you're trying to do, and we'll talk about that a little bit later. Okay, so the next stage is disinfection. So if the biological treatment hasn't got it where you need it to go, then obviously disinfection is one of the things that we have to look at. But another big factor before you get to the disinfection point is how much dilution have you got? So if you're discharging into a coastal environment where you've got over 3 log dilution, chances are normal wastewater treatment, conventional wastewater treatment is enough. But if you're discharging directly into a river that's now designated as bathing water, you don't have much dilution. And that's what drives the disinfection size. So if we can maximize the other two, we can minimize the amount of carbon and energy and OPEX and everything that we put into disinfection. But if we can't, then that's where disinfection becomes more difficult. So if we can maximize what we can get out of biological treatment, then the other two kind of fall in line a bit. So I thought we'd talk about the 2 other ones first, and then we'll focus on the wastewater treatment. How am I doing for time? Oh, cool, okay. Right, so this is where companies like HR Wallingford and Intertech and Stantec, we also have a coastal modelling group, this is where they come into their own, because one of the most important things that we need to do is figure out what the dilution factor is. Because like I said, if we have a dilution factor of 3, suddenly it cuts down the cost of everything we want to do. If we assuming an initial dilution of not very much, like half a log, we're making a massive disinfection system or bacteriological reduction system. So it's really important to understand the dilution. If you don't have much dilution, then sometimes you can use plume mixing. I don't know how far, if you're discharging into a river but the bathing water's downstream, because hopefully they haven't designated the bit right outside your plant, there is plume modelling and stuff that can help us look at dilution. And just to walk away, well, it's okay. If we're aiming for 6.6, can you still hear me without me? If we're aiming for 6.6 log reduction and we've only got a dilution factor of 0.3, so say, times 2, then, 0.3, this is all logs. Then what you need through the treatment process and disinfection is 6.3 log reduction to get 10 out of the back end. So that doesn't even, 10 times 0.3 log. 5 times 0.3 log is 10, that's where the number comes from at the bottom. If you're trying to get 6.3 log E. coli through a process, that's a lot of disinfection if you've got a conventional treatment process, and you're really looking at an MBR, unless we can demonstrate that we can get more log reduction through biological treatment, get all the solids out and zap it a lot with UV and other things. So the less dilution you've got, the more onerous it is on the disinfection process and the treatment process. The way you've got lots of dilution, so for example in the coastal works, going into the North Sea or something like that, if you've got 4.6 log dilution, so you might be a tiny works going into a river and the bathing waters or the shellfish waters a long way away, then you've got high dilution. Your normal log reduction through a biological treatment process is fine, and so there's various places where the Environment Agency have just said, just secure 2 times 10 to the 5, put in a process like a reed bed or something that will just secure that back end. And then you're not looking at it. So this is the bit of the initial question that says, how much do I need to do in the middle? How much dilution and how much disinfection and biological treatment do I need to do? And it's really set and driven by your dilution factor. So although it sounds like it's at the end and it's not very important, it's actually the first question we ask when we start looking at disinfection and bacteriological removal. And we've done the same calculation for bathing waters and for E. coli levels in bathing water and viruses at the same marker. The thing about viruses, we don't actually measure the concentrations. It's all about just adding up the log reduction. So if we know we've got 2 log reduction through attenuation through dilution, and we get 2 log reduction through, say, our treatment process, then we need half a log in disinfection. It's just adding, and that's it. But we need to be able to demonstrate that to the Environment Agency. I guess I'm focusing quite a lot on the England and Wales bit rather than Scotland and Ireland. But, okay. I wasn't going to go into all the numbers on them. This is more of a demonstration of kind of what I've just been saying. So if you've got really high dilution, so the top end of this table, so the first column is the amount of dilution that you might have in the receiving water. And then the red, yellow and green boxes is how easy it is to do at certain effluent quality. And this is all very hard. This isn't like a design guide, so please don't take it away and start designing. It's an idea of roughly how difficult or easy something is to do. So the green boxes is you should be able to achieve it relatively simply. We still need to do sampling and analysis and all that kind of stuff and the proper design, but it's not so difficult as down the bottom end where if there's no dilution and you're trying to aim for a 5, it's going to be a really difficult thing to meet with a lot more thought going into the process. Whereas if you're at the top end and you've got lots of dilution, you can get secondary treatment or a bit more treatment or a small, a relatively easy to design and understand disinfection system. And I guess here I'm focusing on UV because that's predominantly where all the disinfection's been, but there are other ways of doing things. And we've done some work, especially on with the Yorkshire Water and measuring lagoons around the country, looking at what you can achieve through a lagoon system, an aerated lagoon system and things like that. So that's enough on dilution. Just wanted to say a little bit about disinfection, because this is predominantly where our work has been over the last sort of 10 years, is focusing on changing the way we do disinfection in the UK. With the Environment Agency, we started off with UK work projects about 10 years ago. Why is UV perceived to be so expensive? Why is it so high carbon? Why are we using so much power? And then working with the Environment Agency to change the way that we approach disinfection for wastewater. I think the Environment Agency have got a sort of draft guidance written that we've supported them with. And it's basically moving away from rules of thumb and empirical relationships and things like that, moving towards the same kind of methodology used for reuse and water treatment. It's just the fact that we have bits in our water that we need that provide shielding and things like that, and it's understanding that kind of thing. So it basically follows all international best practice protocols and the guidance that it's just an adaptation of the water treatment side of things. So it's much more rigorous, and it uses validated equipment so we can predict what we're going to get out of the back of a disinfection system. And it's based on things like this graph. I don't know how well you can see the details, but it's a UV dose response curve for 3 different effluents. So you can see that the more solids, so you've got primary BNR effluent, filtered BNR effluent, and the more solids, the harder it is to get down. And for the primary effluent, you can never get down, below about 1,000. But for the filtered one, it's a much lower dose to achieve what you want. So there's a play-off between the level of treatment in terms of solids removal and things like that, and what's in the wastewater, and the amount of power you have to put in to get your level of disinfection. But that's a whole nother day presentation, all that kind of stuff. But that was just. But there is a process now with the Environment Agency for everything since I think it was 2014, where rather than doing things this old kind of measured applied dose way, there's a whole new protocol to go through where you work out the dose rather than the Environment Agency giving it to you. Okay, right. I've got about 5 minutes left. Yeah, brilliant. So the last few slides are focusing on what the title said originally, which is what kind of reduction do you get through treatment processes? And I guess the answer is it's site-specific, it's process-specific. There was a lot of, I think various people have done it. When we worked with CREH for the UK WARE project back in 2012, they had a data set. And they took a lot of data all around the country, but they kind of amalgamated it. So all the crude concentrations were amalgamated, all the effluent concentrations, the processes were amalgamated, but it gave a rough idea, this is this graph on the left, a rough idea of kind of what you could get, but it was all very high level. There's some data from one of our partner water companies in the UK WARE project where they specifically measured reduction over each of their treatment plants, and you can see that obviously on the left you've got membranes and ASPs that they achieve the higher log reductions, and then at the lower end there were things like baths and tricklin filters, and generally suspended growth systems do better, and attached growth systems aren't quite as good. But it all depends on the operation of the site, the loading rates, the wetting rates, and all the things that normal process engineers talk about. There's no difference. But there is a variation. And this is just going into that in a bit more detail. So the graph here is showing data from various activated sludge plants belonging to a water company, and you can see that the green triangles, that activated sludge plant did a lot better. It was getting maybe around 3 as an average log reduction. And the brownie circles wasn't doing as well. They weren't getting quite 2 log reduction. But at the time, no one was really looking into what affects the level of E. coli and enterococci and everything reduction through the ASP. So they're all quite similar ASPs, short sludge age, but they just seem to vary. And actually, if you go to a WERF study that they did in 2004, WERF spent a lot of time looking at this, obviously from the reuse side of things. And for an activated sludge plant, the higher the mixed liquor, the longer the sludge age, the better you'll do. And we've seen quite a lot of that in our projects recently, where we've been working with some long sludge age activated sludge plants in southern water, and the concentrations of E. coli for a shellfish water discharge are much lower than, say, for a short sludge age carbonaceous one. So there's quite a lot of data around that we can use. But basically, it's dependent on all the things that take bugs out, so longer sludge ages and higher mixed liquors. What I've tried to do here is because I didn't want to do a presentation where I just presented a bit of data, because it doesn't help anybody really. So if we look at and EPR 7.01 had some defaults, so the EA document had some defaults that they used that said, use these if you don't have any other data, and everybody used those and calculated the dose, and that's fine. But what happens if you can do better or worse? And so what I've done is, for some of the projects that we've been doing over the last sort of 6 to 8 years, where we have measured the data, I've got some examples. Please don't go away and use it for design, because it's more for an example. But you can see that generally activated sludge plants seem to do better than the defaults, and that's obvious. The EA always taken a precautionary approach, don't they? That's what they have to do. But if we've got a larger site and a lower dilution, it's actually worth going out and measuring it. So when we're playing all these things, you might have a tiny site with a lot of dilution. You go, right, let's go for the defaults. It's easy. But if you've got a massive site and not much dilution, actually investing money in coastal modelling and sampling and understanding what's going on, A, minimises your disinfection plant, but also helps you understand the risks associated with, where's it all going to go wrong? How am I going to meet my disinfection target? So, but generally, ASPs do well. Generally, as you can see with the bath and the trickling filters, well, the trickling filters in our example sites actually did okay, but you can see that the levels of virus reduction are a lot lower. So if you've got a bathing water discharge, that's actually quite a big thing, because what you want is the upstream process to do more virus reduction, because the thing that makes a UV disinfection plant big is virus reduction. You need a much higher dose for virus reduction than you do for E. coli reduction. So, which is the opposite of things like chlorine and chemical disinfection. So, 1 minute, okay. It's okay, I think there's only one more slide up. That's all. So, there's data. Well, we were lucky, we measured some, one of our sites was looking at Nerida, so we went and measured reduction over Neridas, and because no one knew what they would get, because there was no data, really. And we found that they actually did really well. There's a whole other thing about the effect on UV dose response of the particle size stuff that comes off, so that's a whole other conversation. But in terms of virus reduction and bacteriological reduction, Neridas did really well, which is a benefit. But the most important thing is basically it's understanding if we've made an assumption that's too low, so we've made an assumption that you can get, 3 log reduction and it only gets 2, then we're not going to meet our end of pipe target, are we? So it's really important that if either we take a precautionary approach and we understand the risks, or we do sampling and we understand what's going on. But if we also assume a value that's too high, I got them to go around, then we don't want to over-design the disinfection system, because basically that's power. And the one thing that is proportional in disinfection is power, isn't it? It's if you want to double the log reduction, you need to double the dose, and that's double the power. And on a big plant, that's the difference between, say, 1 million pounds and 3 million pounds, that kind of thing. So it does make a big difference. So I guess just to sum up everything, there are 3 key mechanisms for microbiological reduction. It's not just about disinfection, and they're all equally important, and it's all about a site-specific approach. We've got dilution dispersion, we've got disinfection, and we've got reduction over biological treatment. And if we actually treat them holistically, rather than treating disinfection as some bolt-on thing at the end we think about later, we can then come up with the best holistic solution for a site. There's no point putting, say, we're going to build trickling filters or something because it's the cheapest, or a bath or whatever, and then go, yes, we've got a bathing water site and we're a direct discharge. And then we've got to build a disinfection system that needs to do 4 log reduction. We need a nuclear power station to power it. So it's about thinking about it holistically and bringing disinfection back into the fold of wastewater treatment engineering, rather than it being this thing stuck on the end. And all the benefits of looking at something from a site-specific basis rather than defaults, really. Thank you very much.
Thank you, Christy. That was really interesting, really to see the thought process there on achieving the best out of disinfection and how the different treatment technologies can affect that. We've probably got 1 minute or 2 for a couple of quick questions. Yep.
Hello, thank you very much for your presentation. I'm Thea Eakins-Coward from Industrial Phycology. So a lot of information in the media at the moment is about the genetic soup of that's produced and the issues that can be created from that. Do you reduce the chance of this genetic soup if you use, say, you said that if you're using a bacterial process or a membrane process, then that's good at reducing the loading, but then how does that compare to UV, where you're actively smashing up the cell? Is it both the same in terms of these genetic issues, or has there been much work on it?
What do you mean by genetic? This is a really long question, isn't it?
So, as you smash up the cell, you're creating this soup of genetics, which can then be taken in by the bacteria, which then can become resistant to,
different
Well, I guess with
treatment
the biological
options.
treatment bit, it's more to do with, especially with activated sludge plants, and I'm going to get Steve to help me in a minute, because he's going to be much better answering this question than me. It's how it flocculates and agglomerates onto the, that's how it gets taken out. Whereas I guess with UV, you're rupturing the DNA, aren't you? But you're not breaking it up into bits, you're just deactivating it. UV deactivates it. And I'm guessing you're a microbiologist, so you know way more about this than me.
I just know about algae, but I've read about
well,
it.
It's the same thing, isn't it? They're bugs. So, yeah, so it's not, you're not breaking something up and releasing all the bits, as far as I know, but I think I might
basically, I've seen that when we work with microalgae, we get huge reductions in bacterial coliforms and things.
Fantastic.
So
another thing you can add to your...
I'm just using this as a sales pitch, really. I'm just jumping on the end of your
there you go.
huge reduction in bacterial coliforms.
Well, if you could do E. coli, enterococci, and F plus coliphage sorted, and we'll...
Yeah,
we'll
I think
share
we
data.
should look into that. But I was just wondering, is there a benefit of, say, using a biological process instead of using the UV
Well,
because
so the
of this?
biological processes won't get down to the levels that you need.
Okay.
So the biological processes get you down to the 10 to the 4, 10 to the 5 bit, but they won't get closer, and that's where the disinfection bit comes in.
Okay, cool.
So the disinfection bit isn't very good at the top end because you've got loads of stuff in the wastewater. So that's why it's a complementary
balance,
process, all the way through.
Okay, I think that's actually all we have time for, so I'm sure Christy will answer any further questions, but yeah, round of applause, please. Okay, on to the final presentation of the day. Harriet Alford from Stantec.
Right, hello everyone, and congratulations, you've made it, the last talk of the day. Thank you all for not getting the early train, that's appreciated. So, yeah, sticking with the bathing water theme, I'm going to be talking about PFA, performic acid, as an alternative disinfection technology. So, previously, and in most of the EPR 7.01 guidance that Christy's been talking about, really, we've only got two kind of approved methods of wastewater disinfection, and those are UV irradiation, fairly commonly, and then membranes. So if you're hitting those really, really tight targets that Christy was talking about, you're normally in a direct discharge kind of area. And yeah, PFA is kind of the new boy on the block, trying to change all of that, and that's what I'm here to talk about. So, there we go, PFA. Background, we'll talk about the need for it, what's wrong with our UV, what's wrong with these membranes, what is it, does it work, is it ecotoxic, big area around that, and kind of where is it going, I guess. So, I guess Christy's given a pretty good overview, to be fair, of the existing bathing water and shellfish water drivers. I just wanted to pull out the WINEP. And the other driver that comes up a little bit more recently is actually flow drivers and how those link into disinfection too. It's been all over the media lately that we've got storm discharges coming out in places we really don't want to admit it. And there's a whole sort of industry evolving around how we treat that as well. Now, fundamentally, what do people care about? They care about the bits you can see and the bugs that can make you sick. We talk a lot about phosphorus, but is that in the media in the same way? Not really. What Joe Bloggs is worried about is what's going to make them ill and the bits they can actually look at. So flow is a whole new area, but we've also got bathing water drivers. I think we're about 500 million this AMP, and there's a shellfish water driver component as well. So although phosphorus is the bright orange large part of that circle, actually disinfection is a pretty big deal too, if I do say so myself. So yeah, fundamentally we've got kind of three key things that might lead to a disinfection type solution. Those are shellfish waters, bathing waters, and then something about trying to reduce storm spills. The kind of regulation around this is a little bit complicated, but I don't want to get into that right now because, yeah, whole nother presentation. And just one kind of up and coming is this whole inland bathing water business. You've seen it a lot more, I think, during COVID, the rise of the staycation and the rise of people swimming in absolutely crazy places. So that's something that's really coming up, and it's going to hopefully mean a lot more work, a lot more disinfection sites for people like me and Christy. So what's wrong with the status quo? So membranes typically, really, really expensive. Yes, they get down to these stupid levels, but the reason they get down to those stupid levels is that you've filtered them through something with tiny, 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 tiny pores. Now that means you've got, low loading rates, you've got like huge energy costs, and just generally they're expensive. Not to mention that if one of them breaks, that's it, you've got a hole, and the whole thing falls over again. We end up visiting a lot of sites where they've had MBRs, but they've not quite been sized to take the solids loading, and actually that means you've got bypasses or whatever else, which is basically making the whole process irrelevant to a point. Because when you're talking about those 6.6 log reductions, if 10% is going past, you're immediately limiting to 1 log reduction, which frankly is not going to cut it. So that's membranes. And then we've got UV. Generally pretty good, to be fair. There are, I guess, 3 places where it falls down. The first is starting and stopping. There are lamp warm-up times. It doesn't like to be stagnant for very long, so it struggles with turning on and off. That's a problem. Very low UVT is the other problem. So if you think about UV, how it works fundamentally is shining a light at your wastewater. And UVT is a measurement of how much of that light gets stuck, basically, on the way through. So if I've got 2 light bulbs here, beautiful, and my particle is here, I need my light to make it through all of that wastewater and hit the bit in the middle. So if my UV transmissivity is low, then actually all this light's getting absorbed on the way, it's not making it to the middle, and I'm not going to kill that. And that's fundamentally what we're trying to do. So anything that is not impacted by that is going to have, huge benefits. And then the other thing is that anywhere that's small with poor power infrastructure, that sort of stuff, it's quite an intensive process. The permitting is, 99 percentile compliance. You've really got to be sat on it. And if you're in a little site in the back end of nowhere, then that's not necessarily an option. So this is a very simplified version. Don't shoot me, anyone in the room. But fundamentally, how does chemical disinfection work? There's 3 key considerations, which are your retention time, how much chemical you've got in there, and your initial disinfectant demand. So basically what you need is a chemical that's going to kill stuff. You need to be in contact with it for enough time for it to do the killing, and you need there to be not so much stuff in the rest of the water that it's going to use up all that original chemical. So what that graph on the right shows is kind of a rough take on kind of log kill versus time. So you've got an initial sort of shouldering phase, and this is basically reactions with inorganics. There's a certain amount of chemical which will just react really quickly and won't disinfect anything at all because it's being used up in these really fast reactions. You've then got a fairly linear phase of inactivation where your log kill is proportional to your contact time, and this is pretty much what we assume in clean water. And then at the bottom, you've got something which is a bit unique to the darker side of life, which is a shielding and tailing period. So this is where you've got really big lumps, basically, and your chemical is struggling to kind of, diffuse, I guess, to the center of your little lump. So that's kind of what we're trying to look at. So there's a whole load of different chemical disinfectants out there. I'm only going to talk about 3. This is some testing that we did for Scottish Water on a little septic tank site, and we were looking basically at which was the best chemical disinfectant choice. The 3 we looked at were PFA, PAA, peracetic acid, pretty similar as a chemical, and hypochlorite, which is the standard disinfection in clean water. Now, interestingly, what we found, so starting, I guess, from the last one, sodium hypochlorite, the big problem is its ecotoxicity. Even on the clean water side, you get formation of THMs. The EA has a pretty serious stance on it. It doesn't really accept it. You've got to dechlorinate at the end of it because at the end of the day, you're putting halogens into the water, which they're not very happy with. Now, both PFA and PAA are organic compounds, so that's less of a concern, which meant that we were concerned more with the efficacy of them. and also with the kind of health and safety issues. It always strikes me as a bit of a catch-22 if you're trying to pick a chemical disinfectant that you want it to kill absolutely everything but be totally fine with people. It's not really a balance that it's very easy to strike. But what we found fundamentally was that PFA was more effective than PAA. And although in itself PFA is a less pleasant chemical, because it has quite a short life, how it's produced is you react sort of performic acid and hydrogen peroxide. And Chimera, Pete sat at the back over there, have a kind of rig that will actually do this on site. So you're not storing PFA. PAA you do have to store in its kind of native form, which has some pretty serious impacts with respect to your kind of operations on site. So that's why we went for PFA over other options. And yeah, this is kind of a bit of a schematic of a typical PFA dosing rig, as I just mentioned. So we're reacting hydrogen peroxide with formic acid. The major advantage that it has is that it's got this equilibrium reaction, which it forms PFA with. But after that, it actually decomposes into organic compounds. So basically carbon dioxide and water, which is great news if you're the EA, because they're much less worried about discharging carbon dioxide and water than they are worried about discharging chlorine, for obvious reasons. Yeah, a few key considerations, most of which, to be fair, I think I've touched on already. Health and safety, so yeah, they are chemicals. They're not particularly nice chemicals at the end of the day, but they're disinfectants, that's what they're there to do. PFA itself is flammable and corrosive, but like I say, it's only kind of present 15 litres at a time, so pretty small. We've got formic acid, which is kind of similar in level to something like sulfuric, which we do use on treatment works, and hydrogen peroxide, which again, oxidizing and corrosive, but again, used on treatment works, so not new to the industry. You do need, however, all the usual precautions around safety showers, bunding, etc., etc. The other consideration is contact time. This is a reason in my mind that it does tend to work better on smaller sites, because you need kind of 15 minutes or so to get a reasonable effect. And obviously if you're in enormous works of however many litres a second, then that's less likely to be present in an outfall pipe or in a disused tank that you have sat around. Whereas if it's, something smaller, that's more likely. EA approval, and that's a whole sort of knotty bit. At the moment, as I say, we've only got UV and membranes approved. However, the EA are interested. There is currently a trial site in Anglian, which is operational, discharging into bathing waters. It's just how that's going to get into regulation, basically, and trying to get that next step so that it gets officially approved, I suppose. And I'll talk a little bit about some of the work that we've done with a different water company about trying to get that approval from the EA. And then, yeah, a little bit of information on the bottom. It's a DFMA rig, always a bonus, and the power loads and potable water supply generally. Yeah, it's pretty small in infrastructure terms, which is nice. So this is the site that I kind of got involved with. For a nameless water company who said, yes, come and present it, but don't tell anyone who we are. So this is a site which had a CSO, basically, near to a bathing water driver. And basically, we needed about 1 log reduction in enterococci and E. coli on the discharge to try and maintain, I think, what was an already excellent quality bathing water. So it was kind of ensuring maintenance of quality rather than an improvement scheme. And what we did, and we sort of discussed with the EA and went through a few phases of implementing, was basically a 3-phase program of lab test work to try and understand the wastewater demand, the dose required, and then to kind of validate the results. And at the same time, we undertook some sort of storm sampling to make sure that all the test work we were doing was representative of the actual wastewater discharged on site. So the tricky bit, obviously, with a stormwater site is that it never rains when you want it to. Miraculously, on this island, considering that it seems to rain 99% of the time, as soon as you want to sample a storm, sun, you can guarantee. If you ever want a barbecue, just let me know, we'll arrange some sampling, you'll be fine. So what we actually ended up doing was trying to mix final effluent and crude from a local wastewater treatment works to mimic the stormwater quality, basically using our final effluent as rainwater. And we spent quite a while trying to work out exactly how much. It turns out 10 or 20%, give or take. And yeah, you can see here we ended up with a pretty good match between what we were actually testing on and what was coming out in the storms. So that was good. And then I guess the interesting bit, well, I'd like to think it's all interesting, but in terms of E. coli log removal, we looked at the kind of geomean and then what happened at the worst 10% with various sort of confidence intervals. And we looked at that with different PFA doses, basically. And what we found is that even in stormwater with quite high levels of solids and therefore shielding, you could get kind of 2 log reduction at sort of the 25% estimate of the geomean. Yeah, pretty quickly, basically. I think we were doing it in about 10 minutes, something like that. So very good at E. coli removal, which was great news. And enterococci results were pretty similar. So for your kind of shellfish water and bathing water, your standard determinants, this is really good. However, and there's always a bit of a catch, this is F+ coliphage. So Christy mentioned a few minutes ago about the requirement for pathogen removal, and that's typically using viruses. Now, the problem with all of that is which surrogate do you use? Because pathogens is a very, very broad term that covers absolutely everything. And when you're looking at reduction across wastewater treatment processes, F+ is normally the one we use. However, is that appropriate for disinfection is a whole other question. And if it is appropriate for disinfection, not so good for PFA, because we did find that you needed some really, really high doses to get a reasonable log removal. Now, for stormwater applications on a more temporary basis, for intermittent discharges, the requirement for virus removal is not enforced in the UK, so it's less of a consideration, or at least in England anyway. So it's less of a consideration there, but for longer term final effluent applications, this is definitely something that needs to be bottomed out, either through finding and proving an appropriate surrogate, or yeah, well, that's probably the best answer, to be honest. How am I for time? Oh, great. So the next bit, which is the other part that the EA are very interested in, is ecotoxicity. And the problem with ecotoxicity, again, is exactly what do you measure? So, the EA wants to be sure that it's not going to hurt anything at all, and quite understandably, but that makes it quite difficult to get a handle on in lab testing or anything else. Unfortunately, we're not the first place in the world to try and do this. So there's an existing application in France, Biarritz specifically, which is a continuous discharge. And they've been dosing 1.2 milligram per litre with a 17-minute residence time, getting that kind of 2 log reduction of E. coli. And there's a French scientist whose name escapes me at the moment, but he's done quite a lot of research and papers on this and has concluded that the observations made do not reflect an alteration of the chemical quality of the environment. You can tell that's translated, but I think the point stands. And then there's this interesting bit of lab test work done by Chetri et al., which was using Vibrio fischeri, which are like little flies, basically. And they discovered that there was a 10 percentile ecotoxicity limit, so 10% of the species started to feel some effect at a concentration of 0.34 milligram per litre. So that's kind of the numbers we've been working to. And I think since I made, there's also an application now in Paris that has been running for, I think, a year or so, and they've got some good data as well that supports that there's not much in the way of impact. However, when we were trying to demonstrate no detriment, I guess, we were trying to use this 0.34 value as something of a target. We were using some of that initial dilution that Christy was talking about and saying, okay, well, if I discharge at 1 milligram per litre, I can prove to you in my modelling that within 5 metres, that's going to be below 0.3. Is that going to be sufficient? And as part of that, we also measured the residuals at different times, which is what this plot shows. So At the site in question, the average residence time was about 24 minutes in this CSO, and the minimum was about 12. So you can see, kind of depending on the PFA dose, you would discharge different concentrations. So we ended up looking at the bottom end. I think we were going for between 2 and 5 milligram per litre with the initial dilution, which I think I have here. Yeah, so you can see initial dilution of about 3 within 10 metres. So that would get you down below the ecotoxicity limits. And yeah, when you're doing that initial dilution assessment, you do need to make sure your assumptions are reasonably conservative with respect to what flow rate you're discharging and your tidal conditions. And this is all going to be very site-specific. So what this gets you to is something that looks a little bit like this. If you dose 3 milligram per litre to start with, we've got lab curves that say we'll have this concentration after this time. You've then got a kind of dilution factor. We also have a kind of knowledge, or Camira do, a knowledge of how quickly the degradation then will happen in seawater or the environment. So you can kind of prove that 10 minutes after the dosing and 10 metres from the outfall, you're well below the levels to be worried about. So the site in question, we kind of had a few discussions with the EA. They were fairly happy with it, I think. They were at the point of agreeing a trial, at which point it came to light that there were some logistical issues whereby basically the chemical could not be brought to site. So it's kind of been parked a little bit, but as I say, there is now a trial running in Anglian as well. But there are sort of there's some really interesting findings here about what this PFA can do as a disinfectant, and also around what needs to be done to make this implementable as a full-scale permanent installation. So for me, the top one is kind of a given. You need validation testing. All of disinfection is site-specific, so you need to make sure that the chemical works on the site that you're looking at. The second one, which is going to involve a lot of EA involvement, is around monitoring of dosing. How do you make sure it's working on a continuous basis? UV, they have measurements saying, look, the lamp is shining, look, I can see this much light, look, this is what dose is happening all of the time. And that's 15-minute data, which the EA then have every quarter and say, okay, it's working. But if you're discharging, finding the equivalent of that, basically, for a chemical dosing application. And for me, there are some fairly obvious ones around proving that you are dosing this chemical all of the time. Pipe loops, maybe, sampling at the end of an equivalent residence time, that sort of thing. But it does all need to be agreed. Okay, nearly there. So EA approval of that, making sure the sampling is set up correctly, and as always, the health and safety type stuff. So, conclusions and further work. PFA is really good for E. coli and enterococci, but the virus thing remains a little bit of a question mark, which could be a problem for full-scale permanent final effluent installations. We do need to work with the EA to develop a proper permitting approach and to get their approval for that type of installation. But it could be a really, really effective solution for the kind of small rural sites with start-stop flows, with poor power infrastructures, and particularly where discharge volumes are small as well. So yeah, I think that was everything I had to say, and yeah, I'll take any questions.
Thank you, Harriet. Any questions? We've got time for one or two quick questions.
Thanks very much. Sorry, it's Peter Pearce here again. You said one or two, I've got two questions, but they will be quick. With regard to the efficacy with the F+ virus, do you see that same problem with other chemical disinfectants and UV, or is this just unique to PFA? Is the first one.
From the kind of clean water side, generally, viruses are much easier to chemically disinfect than bacteria, which makes that kind of result a bit of a surprise, and it does make you wonder if it is just the wrong surrogate, basically, because F+ coliphage isn't actually the virus, it isn't actually the problem. It's just something we use to model that, typically through wastewater treatment processes.
Right.
So, definitely for chlorine, the kind of CT values you'd expect in a virus for 1 log removal are like 0.5 milligram minute or something per log reduction. It's really, really effective. fundamentally the mechanisms
But is the
shouldn't be
rest
that
class
different.
data for other wastewater disinfection, for UV, for example?
No, so I think normally MS2, I'm looking at Christine, is the kind of UV one. It's,
Yeah.
F-class is very good, but like Harriet said, the removal over of PET of the treatment process is quite established. But it's not the right, necessarily the right sort of we don't, it's not enough, it's not measured in enough quantities of UV, we tend to kill it too quickly.
Yeah, okay.
And MS2 MS2 has a similar response as the F-class very much for PFA and other chemical disinfectants. So it's finding, we've got one of the guys that works for us, he's also a professor at John Hopkins, and he's done a lot of work with PFA for reuse work.
Right.
And because they've got it's about what's easy to measure in our labs, and you can. Most of our labs don't do that very carefully. Universities don't use those.
No.
So they use things like norovirus, which is actually probably one of the things we ought to measure. So they've got norovirus rather than human norovirus, which they can lab culture and actually test this stuff on. And so that's the next part of, I guess, the work we have.
Yeah.
Okay.
What's the surrogate that we can use? Because the big thing, however great it is, we need to be able to respond to the environmental agencies which are with the water or reduction of viruses.
Yeah, you need to find something you can measure. Yeah.
Yeah, it's not a case of being desperate.
Yeah.
There's next steps we just have to work
Okay, okay. Sorry, the second one was that you said that the chemical is made up from peroxide and...
formic acid. Yep.
Yeah, formic acid, yeah. I would raise an eyebrow at peroxide, presumably that's a chemical you couldn't bring on site. But how rapidly is that made up? So basically, if this equipment has to respond to a CSO event,
Yeah,
Does-
it's about,
is it made up
there's a
immediately,
15-minute sort of start-up time to get it running, basically.
so your CSO could be running for 15 minutes before you can start dosing?
Well, the site we were looking at, it had a pumping well, so you'd start it up as the well started to rise, like you'd have a trigger level. And
So you would assume it's going to come up and trigger the high level and then stop
but I mean,
messing
it's site by site, isn't it? You need to find some way of getting that 15 minutes, and
Yeah,
most
okay,
storm
that's what I
spills, to
was
be
getting
fair,
at.
there's
You-
some sort of storage.
You need
but,
this sort of 15-minute
yeah.
lead time. Okay, that's
Yeah.
fine, thanks.
Okay, I think that's actually all we have time for now, so thank you, Harriet. And I believe the poster award is happening next door, is that right, Francis? Yep, so that's happening in 2 minutes' time, so thank you, everyone. I'll call a close to this one. Cheers.